So hi guys, how are you all? So welcome to the 50 most important session. So first of all, good morning, good evening, good afternoon, whatever, at whichever time you are seeing this video. So basically in this video session, we are going to discuss the 50 most important questions for your IIT 2026 exams, and we are going to discuss the chemistry part because I am the chemistry faculty at SciAstra, right? And the point is, you have to see this video or this session in a particular way. Okay, so we are going to discuss 50 most important questions. So that does not mean that you will just see these 50 questions and you will go into the exam that, okay, sir has discussed these 50 questions and these 50 questions will come in the exam. No, right? So basically what I am trying to do is, or what we at SciAstra are trying to do is, we are trying to predict based on the previous IIT pattern, previous year exam pattern, that which questions have the highest probability to come in the this year's exam, right? So basically if we are discussing these 50 questions, it does not mean that we are predicting the paper or we are leaking the paper or something like that. No, right? We are trying to predict the pattern. Even if these 50 questions won't come, the point is the concepts related to these 50 questions are very crucial and they might come, right? So you should not see this video as you will just do these 50 questions and you will go into the exam. You should see this video as you should revise the 50 concepts related to these 50 most important questions. Okay, it's not like if I'm doing the question related to basicity, you will just see that question and you will go. No, revise proper basicity concept that you guys have studied in our classrooms, or maybe you have self-prepared or whatever, right? So revise that proper basicity concept and then go in the exam. That's what this video means. Okay, so rather than 50 most important questions, this video should be 50 most important concepts. Okay, and we are obviously going to discuss each and every question, like from each and every concept that is most important, right? So let's see, without wasting any further time, let's move forward, right? So let's move to the first question. In this question, we have to find the incorrect relationship between these two structures given. So this structure on your right hand side is your Fisher projection, and this structure on your right hand side or your left hand side is your Haworth projection, right? Now the point is, this is your cyclic form of the glucose, hemiacetal form of the glucose. So before drawing the hemiacetal form, let's draw the acyclic form of the glucose. So that acyclic form will be something like this: CHO, CH2OH, 1, 2, 3, 4, right? OH, OH, H, OH, H, H, OH, H. Acyclic form of the glucose, right? You can see say D glucose or plus D glucose, minus D, whatever. So the point is, when this lone pair of oxygen attacks at this carbonyl carbon of the aldehyde group, CHO group, this cyclic structure is formed. But the point is, this carbon then converts into optically active carbon center. Okay, so how is it happening? See, there can be two possibilities. One possibility will be this, another possibility will be this. So oxygen, right? And this will be CH2OH. Similarly, oxygen, CH2OH. Now the point is, the newly formed carbon center is optically active. So the OH group can be at the right hand side and it can be at the left hand side, right? And then rest other groups will be like this only: OH, H, OH, H, then your OH, H, right? Similarly, OH, H, H, OH, OH, H. So the point is, this newly formed center, this carbon center, which is your optically active, this optically active carbon center which I have marked with red, it is your anomeric carbon. Why anomeric carbon? Because when OH is coming at right hand side, okay, this everything that you can see on the right hand side will be below the plane, and everything that you can see left hand side will be above the plane, right? So when this OH is coming right hand side, which means below the plane, this configuration, the configuration of this carbon will be R, absolute configuration R and S. And when it is on left hand side, the configuration will be S. You can also find the configuration 1, 2, 3. So it is forming S, and then the least priority group H is at horizontal position, so it will be R, right? Similarly 1, 2, 3. So it is R, then it will become S because least priority group H is at horizontal position. But the point is, why I'm doing this and why I'm trying to say that is because of these opposite configurations of the newly formed optical center, these two are anomers. So you can say that these two are anomers. Okay. So the point is, the relationship is, and they are C1 anomers because this is first carbon, and this first carbon, this is first carbon. Okay, 1, 2, 3, 4, 5, 6. There are 6 carbon in glucose. First one is aldehyde one. So this converts into optically active center, right? So this becomes C1 anomer. So this is correct relationship first of all. Then epimers. So epimers are the diastereomers which have different configuration at only one optical center. So there are different optical centers. This is optical center, C2 is optical center, C3 is optical center, C4 is optical center, right? But the point is, every other optical center is same if you can see, but the first optical center C1 is different, configuration is different. So epimer you can write have different configuration at only one optical center. So obviously C1 anomer will be C1 epimer as well, and obviously if two compounds have same configuration on all other optical centers but only one different configuration, so it will be diastereomer as well. So these are diastereomers as well. So only thing that is incorrect is C1 anomer but not epimer. So correct answer will be C1 anomer but not epimer, because these are C1 anomer as well as epimers. So we have to find incorrect. So this is incorrect. Okay. So let's move to question number 2. So same related to this concept only, we have to find the Haworth projection for alpha anomer of D-glucose. So I told you right here, this is your alpha anomer, where your newly formed anomeric center is of R configuration, that is your alpha anomer, and where your newly formed anomeric center is of S configuration, it is your beta anomer, right? So you have to find the alpha anomer Haworth projection. I will just draw the alpha anomer first. So this is your okay, fine. So this is your oxygen, then OH, H, OH, H, H, OH, OH, H, CH2OH, and this is your alpha anomer of glucose. Right. So to convert this into Haworth projection, I told you that all the groups on the right hand side, which you can see on the right, are below the plane. So you can say right hand side is below the plane. BTP means below the plane, and the left hand side groups are above the plane. Right. So just convert that. So 1, 2, 3, 4, 5, 6 groups are there. So basically okay, so this is oxygen, then this is first carbon, this is first carbon, so OH will be below, H will be above. Then second carbon, OH will be below, H will be above. Then third carbon, H will be below, OH will be above. Then fourth carbon, OH will be below, H will be above. then your fifth carbon CH2 is obviously always above. That's how we form the Haworth projection of the alpha ionomer. So you can see which one is this? OH below, OH below, OH above, OH below, then CH2OH. So I think A is your answer. Okay. You can again check OH, OH, OH above, OH below, and then CH2OH. Okay. So the point is, again, I'm trying to say that these concepts you have to revise properly. It's not like you will just do these questions and you will be like, fine, done. So if I have explained something, you need to know what is Fischer projection, you need to know what is Haworth projection, you need to know what is ionomer, epimer, what is diastereomer, like glucose acyclic forms, and how acyclic form converts into cyclic forms, hemiacetal forms, and what is alpha ionomer, what is beta ionomer, and then how to convert from Fischer projection to Haworth projection for alpha ionomer, and similarly for beta ionomer, because these types of questions or concepts can be repeated, right, or can be asked. Okay, it's not like only these two questions will be asked, right? So I'm not going to explain this again and again. So from now on, it's unsaid, right? So let's move to the question number 3. So which of the following compounds is most reactive towards SN1 reaction? So for SN1 reaction, the first thing that you should see is your stability of the carbocation intermediate. Why? Because SN1 reaction is this. For example, Rx is your organic compound, this X is your leaving group, okay, and basically a nucleophile comes. So what happens is, first this X leaves and minus X minus. So this X leaves, this leaving group leaves. So basically R will be converted into R carbocation, right? And the second step will be addition of nucleophile. So this nucleophile will be added to RNU. So basically, nucleophilic substitution has happened. Nucleophile is substituting the previous leaving group or previous nucleophile, which was X. So that is nucleophilic substitution. But why it is first order reaction? Because only this step, this is SN1, right? So this means this is first order reaction. So only this step decides the rate of reaction. This is RDS. Okay. And in this step, if you can see, rate is dependent on only this species, reactant, right? So only substrate is responsible for rate of reaction. So rate of reaction will be K Rx to the power 1. If you know kinetics, you know what I am talking about, right? So this is first order reaction, right? The point is, this rate of reaction will depend on the concentration of Rx, obviously, but then again it will depend on the leaving group tendency of X, like how good of a leaving group is X, and then it depends on the stability of carbocation. More stable this carbocation will be, easier will it be to leave the X, and easier will it be to form the R plus. So more stable the R plus carbocation, more will be the tendency of Rx to go into R plus cation, right? And more will be the rate of reaction. So the point is, rate of reaction for SN1, first thing you will check, directly proportional to stability of carbocation formed, right? Carbocation intermediate. Second, then you will see directly proportional to leaving group tendency. Okay, so the point is, first let's check the carbocation intermediates that will be formed. So this I will leave, this Cl will leave, this F will leave, this Br will leave. So in all of them, the intermediate will be formed. In A, B and D, the intermediate that will be formed will be this carbocation intermediate, right? But in C, the intermediate will be formed is this. So if you can see that this intermediate is more stable. Why? Because here the lone pair of oxygen can stabilize the positive charge by plus M effect. Okay, so this is your plus M effect. But here there is no plus M effect, only this can be only stabilized by what? Plus hyperconjugation effect, plus H effect, and there will be minus I effect of oxygen as well. So this is more stable, carbocation more stable, carbocation intermediate, so the compound which will be most reactive towards SN1 reaction will be this. Rate of reaction will be most in this because carbocation intermediate is most stable. So next question is related to electrochemistry, right? So basically in this question a particular cell is given, right? And this is galvanic cell obviously because no external battery is given. So this cell is what? Galvanic cell. There is no external battery, right? It is not electrolytic cell, it is galvanic cell. So you need to understand these things. Okay. So if galvanic cell is there, obviously the reaction that will be happening is spontaneous reaction. If it would have been electrolytic cell, then the reaction would have been non-spontaneous, but this is galvanic cell. So in spontaneous reaction what happens is the electrode or the redox coupled with higher reduction potential will reduce and the electrode or redox coupled with lower reduction potential will oxidize, right? So I can write the electrode will with higher reduction potential will reduce, simple, and the other electrode with lower reduction potential will oxidize, simple. And the point is two chambers A and B are given, so these are half cells A and B having electrodes X and Y. So X is that electrode, Y is your right one electrode, X is your left one electrode. The point is electron flow is from Y to X, and in galvanic cell, spontaneous electron flow will be from spontaneous electron flow is from anode to cathode, and your anode is negatively charged electrode, anode is negative, cathode is positive. Okay, now the point is obviously if electron flow is from negative to positive, current flow will be from positive to negative, and spontaneous current flow is from positive to negative. We all know that, right? The point is the voltmeter reading is showing 1100 millivolts. So this 1100 millivolt can also be written as 1.1 volt. 1.1 volt, right? 1 volt is equals to 1000 millivolts. So divide by 1000, 1.1 volt will be the reading in voltmeter. This means that E cell, voltmeter tells you the value of E cell. E cell means E cathode minus E anode is 1.1 volt. Reduction potential of cathode minus anode is 1.1 volt, that is given. And the point is there are three different redox couples given: Fe2 plus, Fe3 plus, Cu to Cu2 plus, Zn, Zn2 plus. So and basically oxidation potentials are given. See, Fe2 plus to Fe3 plus, so it is oxidizing. Cu to Cu2 plus, so copper is oxidizing. Zn to Zn2 plus, Zn is oxidizing. So oxidation potentials are given, but the point is we generally see reduction potentials. So to convert oxidation potential into reduction potential, we know that reduction potential is equals to minus of oxidation potential, right? So just put these values in negative form. Whatever values are negative will convert into positive, whatever value is positive will convert into negative for reduction potential. That's it. Now we have to find appropriate combination of X and Y. So the point is your X is your what? Cathode. Your X is your cathode here, and Y is your anode here, because electrons are going from anode to cathode. So Y is your anode from where electrons are going, X is your cathode from to where electron is going, right? Then the point is we need to see the redox couple whose difference will be 1.1 volt. So if you see here, if you keep X or Y is anode. Wait. If you keep anode, Zn. So Zn will be oxidizing to Zn2 plus, right? And if you keep X, which is cathode, let me reduce the, okay, wait. If you keep cathode, copper. Copper 2 plus is going into copper. Now the point is, reduction potential of copper 2 plus to copper will be 0.34 volt because oxidation potential is minus 0.34 volt. So reduction potential will be 0.34 volt, and reduction potential of Zn2 plus to Zn will be minus 0.74 volt because oxidation potential is given 0.7476 volt. So it will be minus 0.76 volt. So the point is, put these values in your E cell value. So here you can find E cell, E cathode 0.34 volt minus of 0.76 volt. So this will be 0.34 volt plus 0.76 volt. So answer will be 1.1 volt or 1100 millivolt. So your Y is your zinc, X is your copper, C is your answer. Is this fine? So you need to understand all these concepts. What is electrode, what is cathode, anode, spontaneous electron flow, galvanic cell, electrolytic cell, right? And spontaneous electron flow, spontaneous current flow, E naught value, E cell is equals to E cathode minus E anode, and that E cathode and E anode are reduction potential, not oxidation potential, right? So basically you need to know these things. So then the next question is your basically reaction coordinate curve is given, right? Potential energy is shown on y-axis, reaction coordinate is shown on x-axis. You would have seen these kinds of graphs and curves in chemistry a lot, right? So reaction between H2 and I2 is given to form HI. Okay, so energy profile diagram is given. This is exothermic reaction, which means the energy of HI is less than energy of H2 and I2. Basically, energy of product is less than energy of reactant. That is why it is exothermic. Now the point is, this is your activated complex that will be formed, right? So those are your reactants. This is your product. The statement which is incorrect we have to find, right? So release of energy is 26.46 kilojoule per mole. So that is delta H value. Delta H is equals to minus 26.46 kilojoule per mole. Okay, that has been given, that this much energy is released. Now the point is, we have to find the incorrect enthalpy. So incorrect statement, sorry. A part is enthalpy of formation of 2 moles of HI. So this is for 1 mole. So formation of HI is given, but the enthalpy of formation is for 1 mole, which is given here, right? So for 2 moles, you have to multiply. So you have to multiply this by 2. So this will be 26219215 kilojoule. So if I convert into joules, 5292 joules, 52920, sorry. Okay, you have to multiply by 1000, right? So this is your correct statement. We have to find the incorrect statement. Now the activation energy of reaction is exactly equal to total energy of the activated complex. So total energy of the activated complex, this is your total energy of the activated complex. Activated complex is the complex with the highest energy, this. Transition state, which you call, right? So this total energy of the activated complex is your threshold energy, not your activation energy. This is your ET, threshold energy. Okay, what is activation energy? Activation energy is the energy required by reactant to form the transition state or activated complex. So energy required by reactant. So reactant is already there. So this is your activation energy. This is the energy required to reactant to form activated complex. So this is your activation energy, EA. Okay, so the incorrect statement is this one, right? Let's still see C and D. The log of rate constant for this reaction decreases linearly. So log of rate constant. So we know what is Arrhenius equation. Arrhenius equation. So in Arrhenius equation we see K is equals to A e to the power minus EA by RT, right? So we take the ln form. Ln K is equals to ln A plus or minus whatever minus EA by RT. So basically that is what is happening, right? So you convert it into log. So 2.303 log K. So this is A into B. So what I have done is ln A into B is equals to ln A plus ln B, right? That's what I have done. So ln A plus ln this e to the power minus EA by RT. So ln e to the power minus EA by RT is minus EA by RT. Okay. So you convert into log. Ln is equals to 2.303 log. So 2.303 log A minus EA by RT. So log K, 2.303 will go there. So this will be log A minus EA by 2.303 RT. So this will be your equation. So log K, log of rate constant of this reaction decreases linearly. So this is your equation. Y is equals to C minus mx. So C is your log A, which is your y-intercept. Y is your log K. M is your minus EA by 2.303 R, and x is your 1 by T, inverse of temperature, right? So x is your 1 by T. So as this 1 by T, you can also write this as, wait, you can also write this as 1 by T. Okay. So as this 1 by T increases, this whole value EA by 2.303 R into 1 by T, it will also increase. This 1 by T is increasing, na? This whole value will also increase, but this whole value is in negative. So this log A minus this value, the result will be smaller. So log K will be smaller, right? So 1 by T increases, log K decreases. That is what is written. Log of rate constant of this reaction decreases linearly as we increase the inverse of temperature, as we increase 1 by T, right? So that is what has been written. So this is also right. Threshold energy of this reaction is exactly equal to total energy of the activated complex. So total energy of activated complex is threshold energy. That is what I have told you. So D is also right. So the incorrect option is your B. Okay. So let's move to next question. In this question, basically, they have given the absorbance versus wavelength curve. So different wavelengths and absorbance of different complexes have been given. So the point is lambda max is given for different complexes, right? You can read the question. So lambda max is the wavelength at which a particular compound will absorb the maximum. So in your coordination complexes, lambda max or wavelength absorbed by the coordination complex is obviously inversely proportional to energy absorbed, right? Because energy is inversely proportional to wavelength but directly proportional to frequency. So this energy absorbed is directly proportional to del O value. If the octahedral complexes are there, the energy gap between T2G and EG orbitals, that is del O. This is del O. T2G, EG. So this is your del O, right? So higher this energy gap, more will be the energy required for electron to excite. So more will be the energy absorbed. More will be the energy absorbed, lesser will be the lambda max. This lambda absorbed is your lambda max, nothing else. Okay, so the point is lambda 1, lambda 2, lambda 3 are the lambda maxes and particular compounds are given. So this del O value or crystal field splitting, whatever you want to call this as. First you will see oxidation state of metal. So higher this oxidation state, more will be the del O value. Second you will see period number of metal atom. If oxidation state is fine, if oxidation state is same, then you see the period number. So period number means down the group. So third period 3D series, fourth period 4D series, fifth period 5D series, that's why. So higher this period, like 4D series will have greater del O value than 3D series, right? And then at the last you will see ligand field strength. You see spectrochemical series of ligand, right? Ligand field strength. So here first let's see the oxidation state. So oxidation state in complex CONH3 2 positive. So oxidation states are CO2 positive and then FeNH3 3 positive, FeCN6 3 negative. So in both the complexes Fe is in +3 oxidation state. So 3 metal atoms are there or metal ions are there, CO2 positive, Fe3 positive, Fe3 positive in 3 different complexes. So basically these two you can't compare based on the oxidation state. So then you will have to see the period number. So Fe, same period, same ion. So oxidation state and period number you can't compare. So you can only compare based on third. Ligand field strength. But cobalt 2 plus and Fe3 plus you can compare based on the first point itself. Oxidation state is different. So oxidation state of Fe3 plus is higher. Fe3 plus oxidation state is higher compared to CO2 plus. So in that case Fe3 plus and CO2 plus, Fe3 plus del O value will be higher. So Fe3 plus del O value will be higher. So energy absorbed will be lower. So basically lambda max will be lower. So cobalt 2 plus lambda max will be higher. So this lambda 3 highest lambda max is of cobalt 2 plus. Okay, then we have to see lambda 1 and lambda 2. So if you can see two complexes, two different ligands, Cn minus and NH3. So ligand field strength for Cn minus is higher or much higher than NH3. So this ligand field strength for Cn minus is higher, which means del O value for FeCN6 3 minus will be higher, which means more energy absorbed, which means lesser lambda max. So this least lambda max, lambda 1, will be of FeCN6. So lambda 3 will be of CO NH3 6 and in the middle is FeNH3 6 3 positive. So your answer is D. Okay, so let's move on to or next question, whichever question number this is. So correct phenomena which caused only marginal difference in the radius of 5D as compared to 4D. So this is your atomic radii of D series elements like 3D, 4D, 5D series, right? So as you go from 3D to 4D, here, see, there is a very high gap between atomic radius compared to as you go from 4D to 5D. So basically you can call this as 3D. Green one is 3D, blue one is 4D, red one is 5D. So you can see the gap between 4D and 5D is very less compared to 3D. Now the point is what happens like that. Okay, so in 3D series, The electronic configuration is your 4s 3d, right? That is the electronic configuration. In 4d series, the electronic configuration is 5s 4d, right? But in 5d series, electronic configuration is 6s 4f then 5d, right? So you can see then when you go from 3d to 4d, the electronic configurations are similar, like 4s 3d, 5s 4d. But when you go from 4d to 5d, extra 4f orbitals come in between. So when you go from 4d to 5d series, 4f orbitals are present. And because of this 4f orbitals, we all know that f orbitals have the least shielding effect, right? So very poor shielding effect compared to sp and d. So poor shielding effect. What is shielding effect? Basically, they can't shield the outermost electrons from the nucleus pull, right? So that is your shielding effect. It has very poor shielding from nucleus pull. That is why the nucleus will pull the outermost electron more tightly. So the size of 5d series will decrease. It will increase, it will be more than 4d, but the point is it will not increase that much because there is 4f orbitals as well. So these 4f orbitals will cause very poor shielding. So, and this phenomena is called as Lanthanide contraction. In reality, this phenomena is not called as Lanthanide contraction. Lanthanide contraction is observed among lanthanides, okay, not in D series elements. So lanthanide contraction is how the size of lanthanides, subsequent lanthanides, when we go from left to right, decreases very much. It should decrease, it will decrease when we go from left to right, but it decreases very much more than the predicted trend. Why? Because 4f orbitals are there in lanthanides. So basically they have very poor shielding effect. So that is lanthanide contraction. This is not lanthanide contraction, but the question is such that you have to mark the right answer like that only. So lanthanide contraction due to poor shielding effect of 4f orbitals. Okay, so let's move to next question. So basically this is a structure of 3-methyl cholanthine, whatever it is, I don't know. Okay, so how many sp3 carbon atoms are there in this compound? Okay, so we have to find the sp3 carbon atoms. So one is this, another is this, another is this. Rest all others have a pi bond. So sp3 carbon, I don't think that I need to explain what is sp3 carbon. So any carbon which has 4 sigma bonds. sp3 carbon is any carbon which has 4 sigma bonds. Okay, it should not have any pi bond, right? So that is your sp3 carbon. So 1, 2, 3, right? So answer is 3. Okay, so let's move to next question. So basically in this question we have to find the major product Q. Okay, so first one is addition of halogen in the presence of UV. So if UV would not have been present, this halogen would have been added to the alkene, right? But the point is here UV will be present. So because of this UV, the mechanism that will be followed is radical mechanism. Okay, so what will happen? This Br2 will convert to Br radicals. The bond will be broken and the radical will be formed. This Br radical will then attack on the substrate, which is your DDCH3H2CH3. So this Br radical will attack on this substrate. So basically it will take hydrogen or deuterium, whatever it is, or it can take other atoms as well, but the point is it will form a radical. So the radical that will be formed, the radical intermediate that will be formed out of this substrate should be the most stable radical intermediate. So the point is here on CH3, 3 hydrogens are there and there is 1 deuterium. So the point is this Br can attack on this deuterium, this Br can attack on this hydrogen, this Br can attack on these hydrogens or any other hydrogen. The point is whatever hydrogen you will leave or you will make leave, you will form a radical species. So that radical species should be the most stable radical species. So the most stable radical species that will be formed will be this only. See. This radical species. Are you able to understand? If you would have made this one as a radical species, then there would have been just plus R effect, right? Here there is plus R effect, right? As well as there is hyperconjugation effect from these hydrogen, right? Right? Are you able to understand me what I am trying to say? So the point is, the most stable radical species that will be formed is your this radical species. So once this radical species is formed, now what will happen? Or this dBr will leave, so minus dBr. So this dBr is left, and then another Br will attack on this species. BRD. So this will be your P. Okay. So this is your P. So this P will then attack on dBr that is left. See, in the presence of CCl4. dBr CCl4. So now this alkene will attack at the deuterium, right? And positive charge will be formed here. Positively charged intermediate will be formed here because of the hyperconjugation effect of 3 hydrogens here of the methyl, and D will be attacked here, or D will be added here. Then Br minus will attack here. So the final product that will be formed is dBr, Br, D, something like this. Okay. Are you able to understand? So the final product will be dBr, Brd, C, if you can see. Okay. If this would not have been UV, then the mechanism would have been different. It would not have been a radical mechanism. It would have been a halogen addition to alkene. Okay. So next question. So which of the following electron flow orbital diagram correctly represents synergistic effect of metal carbonyl interaction? So synergistic effect is what? So in your coordination compounds, ligand and metal are bonded together, right? So what happens is synergistic bonding what happens is this metal and ligand will form bond, coordinate bond, but point is the first bond that will be formed is from ligand to metal. So ligand donates its or shares its lone pair towards metal, so to form a sigma coordinate bond. So that is the first bond. So this is known as dative bond. Okay. Then the point is there are two conditions to be followed. If the metal contains donatable electron group and if the ligand contains accepting orbital. So first thing is metal should contain donatable electron density. Second thing is ligand should contain accepting orbitals of suitable energy. If that happens, then metal will donate or share its electron pair with your ligand because it can accept. So what will happen? Second bond will form from metal to ligand, that will be pi coordinate bond. and that will be your back bond. That is known as back bond. So sigma coordinate bond is known as dative bond, pi coordinate bond is known as back bond. So because of these two bonds formed, dative bond and back bond formed, the bond between metal and ligand is very strong. But obviously that will only happen when your metal contains donatable electrons and ligand contains a particular suitable energy orbital to accept the electrons. So this whole arrangement is known as synergistic bonding. Now in CO, I won't be telling you the complete molecular orbital diagram of CO, but you need to understand one thing, that in CO, HOMO and LUMO, HOMO is highest occupied molecular orbital, LUMO is lowest unoccupied molecular orbital. I should write it somewhere else, a better position. CO ligand, HOMO and LUMO is your pi star orbital. Okay, so in the first bond that is formed from ligand to metal, in which CO will share its electron pair to metal, right? So it will share from HOMO. So this HOMO is used for dative bond, or I should say electron sharing, electron donation, whatever. So when this HOMO is donating or sharing its electron pair to ligand to form sigma coordinate bond or dative bond, so electrons are going from pi star. So what happens is, I should write in CO, when dative bond is formed, electrons are going from pi star, so this increases the bond order of CO. So CO bond order is also increased, and bond order is increased from metal to carbon as well, because bond is formed between metal and carbon, so obviously bond order will be increased. But the point is CO bond order will also increase, the bond order of C and O. Okay, but the point is, when metal will share its electron towards CO, okay, to form back bond, so it will donate in lowest unoccupied molecular orbital, which is again pi star. So this pi star will accept electron when back bond will be formed, and because it accepts electron in pi star, bond order between CO will decrease, but bond order between metal and carbon will still increase, because second bond is being formed between metal and carbon, but bond order between C and O will decrease because pi star is accepting electron. So I will write back bond bond order between CO decreases, but bond order between MC increases. So the correct representation, this is the extra information that things can be asked. So the point is, that is not related to the question, but the question is correct representation will be D. Why? Because here you can see CO, first it is donating its electron pair, right, to form sigma coordinate bond from pi star, and second, metal is donating electron to CO from its pi orbital to the pi star orbital. So basically that is what has been explained by me, right? So the correct representation will be D only. You can see any other representation. So in this representation, both the electron pairs are being donated by metal, so this is wrong. In this representation, first sigma coordinate bond is donated from metal, so obviously this is also wrong. In this representation, both the electron pairs are donated from ligand, that is also wrong. So the correct representation of synergistic bond is D. So next question, we have to explain the stability of alkenes. So there is a rule known as Brett's rule that you should know. So Brett's rule it states that the carbon or the bridgehead carbon in any polycyclic compounds or bicyclic compounds or bridged compounds, whatever, the bridgehead carbon, so these are the bridgehead carbons. If you see these are the bridgehead carbons. So the bridgehead carbons will never ever attain sp2 hybridization. So bridgehead carbon will not attain sp2 hybridization. Now sp2 hybridization can be attained by two things, maybe more things, but two things that we have to see here are, first, that carbon can't be a carbocation, so carbocation also has sp2 hybridization, and that carbon can't also have a pi bond, because pi bonded carbon atom is also sp2 hybridized carbon, only one pi bond. If any carbon has one pi bond, it is sp2 hybridized carbon. If it has two pi bonds, then it will be sp hybridized, but that is fine, right? So the point is, if you can see, there is one pi bond at bridge head carbon, right? So this will be very unstable, so this will be least unstable alkene. Now comparing A and B, if you see B, there are 1 2 hydrogen, 1 2 hydrogen, 1 2 3 hydrogen, right? But in A there are only 2 alpha hydrogens. So for A only 2 alpha hydrogens are there. For B 2 2 4 7 alpha hydrogens are there. So more alpha hydrogens means more plus H effect. So more plus H effect will stabilize the B alkene most. So most stable alkene will be B, then A, then C. C will be the least stable alkene, right? So let's move to next question. So this question is about the electrophilic substitution reactions in phenol. So let's draw phenol first. So what happens is, in electrophilic substitution reactions of phenol, so phenol will act as a nucleophile obviously. So this lone pair of phenol gives plus M or plus R effect, whatever you want to call it as, right? It's one and the same thing, right? So because of that plus M or plus R effect, whatever, this ring, this whole benzene ring acts as a nucleophile. So minus charge is on ortho and para positions. So ortho and para positions have high electron density, right? So because of this high electron density, it will attack on electrophile, right? From ortho or para position, whatever, and then electrophile will come on ortho or para positions, whatever. So I am just representing it like this. This representation means that it can go in like any carbon, like ortho, para, whatever. So the point is, since the rate of electrophilic substitution depends greatly over electron density on the benzene ring, obviously I told you, higher the electron density, higher the nucleophilicity of this benzene ring, more will be the rate of reaction of this electrophilic substitution reaction. We have to find the correct statement. So faster electrophilic substitution is expected in orthonitrophenol. So if you are adding electron withdrawing group to this benzene ring, electron density of this benzene ring will decrease. So if electron density or nucleophilicity of this benzene ring will decrease, rate of reaction for electrophilic substitution reaction will decrease. And if you add electron donating group, so this will increase the electron density further, right, of this benzene ring, which will increase the nucleophilicity further, so which will increase the rate of reaction for electrophilic substitution reaction. So this will increase the rate of reaction for electrophilic substitution reaction. This will decrease the rate of reaction for electrophilic substitution reaction. So in statement first, they have said about nitro. So nitro is electron withdrawing group, nitro. This nitro is your electron withdrawing group. So this electron withdrawing group will decrease the rate of reaction. So faster electrophilic substitution will not be expected, slower will be expected, right? So this is incorrect. B is phenol reacts faster with electrophiles. If phenol reacts directly with electrophiles, so this is direct reaction with electrophile. But C is phenol reacts faster with electrophiles if phenol reacts first with KOH. So in KOH, if you react phenol first with KOH, this OH will take this hydrogen, acidic hydrogen, right? So if this will take this acidic hydrogen, this will turn into phenoxide, anion. Okay, so this phenoxide anion will be more nucleophilic. Why? Because this plus R effect will be more stronger because O is containing a negative charge. So because of this benzene ring will be highly nucleophilic. So because of this higher nucleophilicity, the rate of reaction will increase, right? That is what has been written. Phenol reacts faster with electrophiles. If phenol first reacts with KOH, then with electrophiles. So that is your correct statement. So we know the correct statement, but let's just see the D statement as well. The formation of phenol from chlorobenzene is example of electrophilic substitution. So from chlorobenzene, so let's take so they are saying from chlorobenzene they are forming phenol, right? So basically you will have to react with NaOH here, right? So when you will be reacting chlorobenzene with NaOH, this OH will attack here, right? And this bond will break, but then this bond will again go. So what will happen? Something like this. Cl, OH, this bond will break, but this bond will again, negative charge will again go back and Cl will leave. So basically this Cl will take this H as well. So basically what will happen? What will be forming? O minus Na plus. So after that you have to do the acidic hydrolysis, not hydrolysis, what I am saying, acidic workup. Okay, so after that this phenoxide ion will be converted into phenol. Okay, so this is not your electrophilic substitution reaction. Okay, this is your nucleophilic substitution reaction. OH is a nucleophile, it is not an electrophile. OH is attacking on benzene ring. So benzene ring is acting as an electrophile here. So this is your nucleophilic, kind of nucleophilic substitution reaction. So nucleophilic substitution, but even after nucleophilic substitution you won't get the phenol. You will get phenoxide ion. You have to do acidic workup. So you can't just say it as nucleophilic substitution, but the point is it is not electrophilic substitution for sure. So this is also wrong, so your answer will be C. So let's move to next question. In this question, aqueous solution of NaCl is given, correct relationship of its osmotic pressure with its volume at constant temperature and amount of substance. Okay, so osmotic NaCl solution is given and we have to find correct relationship of its osmotic pressure of this solution. So osmotic pressure of solution will be equal to I is Van 't Hoff factor, right, into concentration of solution into RT, right? So this is your osmotic pressure formula. The point is we have to find the correct relationship with at constant temperature with volume. So we have to open this concentration. So generally this concentration is taken as molarity. So this concentration of solution can be written as number of moles of solute divided by volume of solution. If it's in liters, it's fine. If it's in ml, you will multiply by 1000 above, but whatever it is. So you can just write pi is equals to I nRT by V, right? So you have to find the relationship with not velocity, volume. The point is, see, chemistry and physics are not, very different. So I seldomly study a lot of physics and I explain physics as well in my chemistry classes and all that stuff. So my chemistry classes are not just chemistry. There is a lot of physics and maths as well. So that's why I just, said velocity, because I come across velocity and speed a lot. So yeah, fine, no worries. So this is volume V. So they have said that temperature is constant. Obviously N is also constant, R is also constant, Van 't Hoff factor is also constant, or it is assumed as constant, whatever. So you can write this as I nRT into 1 by V. So this whole thing is constant, so you can call this as pi is equals to K 1 by V, and you have to see the graph between 1 by V and pi only. Pi is osmotic pressure. So this is your directly proportional graph, right? Y is equals to mx plus c. Mx plus c. C is 0. Y intercept is 0. M is your k, whatever is the constant. X is your 1 by V, 1 by volume. Y is your pi. Right? Is this fine? So it will be directly proportional graph. So only graph of direct proportionality is B, but the point is this graph is also not 100% correct. Why? Because, it's correct. See, this graph is not touching the origin. If you will see this properly, it is, a slightly bit above origin. Okay, if this would have been touching origin, then this would have been wrong, because at origin 1 by V is 0. So 1 by V 0 meaning V infinity, and volume can never be infinity, right? But the point is, even if it is infinity, I'm not saying that this is completely incorrect graph or whatever. Even if it is touching origin, the point is direct proportionality graph will be this only. Okay, maximum to maximum it can be like this, something like this, or it's fine. Even if it is given in the question, it's fine like that also. Okay, it's not a big deal. Okay, so let's move to next question. So this is a second order reaction. We have to find, or P, Q, R are given. 3 variations are given. Q is with catalyst, R is with catalyst, and R is with catalytic poison. Okay. So P is without catalyst. Okay, P is without catalyst, Q is with catalyst, R is with catalytic poison. So catalytic poison and negative catalyst are different things. Catalytic poison renders the catalyst inactive. Okay, so, and catalytic poison will decrease the rate of reaction as well. Okay, so catalytic poison is different thing, right? So it is kind of a negative catalyst, right? So it will decrease the rate of reaction. P is without catalyst, and Q, wait, let me see first. Okay, so P is without catalyst. Okay, Q is with catalyst. Okay, R is with catalytic poison. Okay. So R is a poison. So obviously it will increase the activation energy. So it will increase the rate of reaction. Q is a catalyst. So it will decrease the activation energy. It will decrease the rate of reaction. P is simple, right? And this is a exothermic reaction. So these graphs cannot be true. This is endothermic. This is endothermic. And this graph can also not be true, because catalysts never change the energy of the product or reactant. So catalyst only changes activation energy, but not the energy of reactant or product, whatever it is. So it does not change the energy of reactant or product. Okay, so this is also incorrect. So only option is D. And if you have to compare the rate of reactions as well, you can compare the rate of reactions. I told you R is catalytic poison, so it will increase the activation energy. The rate of reaction will be minimum in R. So activation energy is this. So activation energy in R is maximum. Q is catalyst, it will decrease the activation energy. So you can see minimum activation energy in the case of Q, so increase the rate of reaction, and P is somewhere in between both. It is without catalyst as well as without the catalytic poison. So it won't have that much high activation energy as catalytic poison R, but it won't have low activation energy like Q. So it will have intermediate activation energy and intermediate rate of reaction. So D is your correct option. So again, a question related to catalyst. In the presence of a catalyst, which of the following statement is correct? So catalyst increases the rate of both forward and backward reaction. So if a particular reaction is going on, let's suppose A, B, C, D. This particular reaction is going on. So the reaction is possible in forward direction as well as in backward direction. So the forward direction reaction will have some activation energy of forward reaction. Backward direction reaction will have some activation energy of backward reaction. So the point is the catalyst acts both on forward and backward reaction equally. So it decreases the activation energy of both forward and backward reaction by equal amount. So catalyst decreases the activation energy forward and activation energy backward by equal amounts. Okay, that's why it will increase forward rate of reaction and backward rate of reaction by equal amounts, right? So that is why C is your right option. Let's move to the next question. In this question, we have to find the compounds which are not aromatic. We don't have to find non-aromatic compounds. We have to find compounds which are not aromatic. So if you can see, this is your 10-aniline. So 10-aniline obviously has, it is a very special case, right? It has 2 hydrogen atoms which are known as flag pole hydrogen atoms. Okay, so these hydrogen atoms repel each other. They repel each other, right? So these hydrogen atom, when it will repel each other, so basically 2 carbons are like that. So these are carbons and then there are hydrogen attached to these carbons. So they will repel each other. So this carbon will go downwards, this carbon will go upwards. So hydrogen attached to this carbon will go downwards, hydrogen attached to this carbon will go upwards, if you can imagine what I am trying to say. So the flagpole repulsion is decreased like that. Why? When these carbons go out of the plane, one above the plane, one in the plane, the molecule is not planar anymore. And if the molecule is not planar, okay, so this is not aromatic. Okay, non-aromatic and not aromatic. This is both not aromatic and non-aromatic. Okay, you can write it as non-aromatic or not aromatic, whatever. This is both. Okay, then if you see this next compound, here in such kind of compounds you ignore the pi bond in the middle of the compound. You always see the pi bonds in the periphery. So like this, because why? Because this periphery pi bonds will be involved in complete cyclic conjugation, right? 1, 2, 3, 4, 5, 6, 7. So how many pi bonds are there? 1, 2, 3, 4, 5, 6, 7. So 7 pi bonds are there. This means 14 pi electrons. And for being aromatic, you have to follow Huckel's rule of aromaticity. So 4n plus 2 pi electrons should be there. 4n plus 2. So this is 4 3s are 12 plus 2. So n is 3 here. Okay. So obviously it is planar. It has 4n plus 2 pi electron. There is complete cyclic conjugation in the pi electron. So this is aromatic. Okay. Then obviously this is pyrrole. This lone pair will be involved in conjugation. So there are 6 pi electrons. So obviously this will be aromatic A. Completely planar molecule, cyclic conjugation is there. Then in benzene there is only 3 pi bonds. This third bond is not a pi bond. This is formed due to the overlap of these sigma bonded electrons. Not sigma bonded electrons, what am I saying? Due to overlap of this hybridized orbitals. So pi bond is formed by overlap, sidewise overlap of unhybridized orbitals. So this pi bond is formed by the overlap of this sigma, or you can say hybridized orbitals, right? So these are not involved in conjugation. The only pi bond is involved in this conjugation is this one. So basically, just like benzene, it has 6 pi electrons and complete cyclic conjugation and planar. So this is also aromatic. Now, then this is cyclobutadiene, not butadiene. Okay, not butadiene. Yeah, cyclobutadiene, right? So the point is here 4 pi electrons are there. So 4 n pi electrons are there, right? N is 1 here. So the point is this is completely cyclic. Complete conjugation is there, cyclic conjugation is there, planar molecule, but the pi electrons are 4 n pi electrons. So this is anti-aromatic. Anti-aromatic, right? Now this one, cyclopropenyl cation, whatever. So the point is here, obviously this carbocation is sp2 hybridized, and here the pi bond can be conjugated to the carbocation carbon, right? So the pi electrons here are 4n plus 2 pi electrons. Why? Because 2 pi electrons are there, right? So 4n, n will be 0 here. So only 2 pi electrons are there in this molecule, and it is in complete cyclic conjugation. The molecule will be planar, so this will be aromatic, right? But the point is this is octatetraene, so this is a tub shaped molecule, something like this. Okay, so this is not a planar molecule, this is a tub shaped molecule, although it has 4 pi bonds, so obviously it has 8 pi electrons. Even if it would have been a planar molecule, this would have been an anti-aromatic molecule because it has 4 and pi electrons. But the point is this is not planar, so this is not aromatic, not non-aromatic, not aromatic. Not aromatic or non-aromatic, whatever. So this is not aromatic, this is anti-aromatic, right? This is non-aromatic, so not aromatic. This is non-aromatic, so not aromatic. So in the question we have to find not aromatic. So in that, non-aromatic as well as anti-aromatic compounds will be given. So 3 will be the answer. This one, this one, this one. So these are not aromatic. Okay. So in this question, we are given different compounds having pi bonds. So first one is benzene, third one is your 1,3,5 cyclohexatriene, and this is a hypothetical molecule. In this, these pi bonds are not in conjugation, cyclic conjugation. Basically there is no resonance involved, so basically this is not aromatic. No aromaticity is involved here. But this first one is aromatic. So pi bonds are in complete cyclic conjugation, there is resonance basically. So order of release enthalpy of hydrogenation we have to find. So what is hydrogenation? Hydrogenation is basically when there is a pi bond, you add hydrogen molecule to it. So this pi bond will take this hydrogen molecule, right? So one pi bond will be broken, this pi bond will be broken, and 2 new sigma bonds are formed. So why is energy released? To break a pi bond is weaker than sigma bond. So to break a pi bond, you need to give some energy, and when a sigma bond, a stronger bond is formed, some energy is released, and 2 sigma bonds are formed first of all, and 1 pi bond is broken. So bond broken, 1 pi bond which is weak, and bond formed, two sigma bonds which are strong. So more energy is released, so overall energy is released. This means the process is exothermic. right? The point is, how do we measure or compare the energy released in different compounds? So more the number of pi bonds that will be broken, so more will be the energy released, right? So this energy released is directly proportional to first number of pi bonds. Second, this energy released is inversely proportional to conjugation of pi bonds, or you can say inversely proportional to stability of pi bonds. More stable a particular pi bond is, more will be the energy required to break that pi bond, right? So more or so lesser will be the energy released. So if you see, in both of these compound 1 and 3, there are 3 pi bonds. In 1 and 3, there are 3 pi bonds. In 2, there is only 1 pi bond. So obviously in 1 and 3, more energy will be released. So in second, the least amount of energy will be released. So D and A are incorrect. Now let's compare B and C. So third and first energy will be same? I don't think so, because in first there is complete cyclic conjugation resonance. So the pi bonds in first are more stable. Pi bonds in first are more stable. It is aromatic. So it will be difficult to break the pi bonds compared to third one. Okay, so you need more energy to break the pi bonds of first. So basically, lesser energy will be released in first, so more energy will be released in third, so B will be your answer. Okay, so let's move to the next question. The order of basicity of the following compounds. So basically, the basicity will be directly proportional to the tendency to give lone pairs, right? So basicity is directly proportional to tendency to give lone pair, right? So in this question, you can see this nitrogen is sp3 hybridized, right? This nitrogen is sp2 hybridized, but obviously the lone pairs are localized. They are not delocalized. Basically, there is no conjugation. So in both of these, there is no conjugation, right? And in third one, obviously it is pyrrole. So there is obviously conjugation. This is aromatic. So for this compound to become aromatic, the lone pair of nitrogen should be delocalized. So there is highest conjugation or delocalization in this compound compared to any other compound in this list. So highest conjugation of lone pair. Now this lone pair will also be going into conjugation or delocalization, but the point is this benzene is aromatic. So if this will go into conjugation, right, so it will break the aromaticity. So this one is aromatic, not this benzene ring is aromatic. So lesser conjugation of lone pair, because this conjugation will break the aromaticity. So lesser conjugation of lone pair. Simple. So no conjugation, lesser conjugation, highest conjugation. So highest basicity should be here, right? But the point is this is sp2 hybridized. So sp2 hybridized nitrogen will be more electronegative compared to sp3 hybridized lone pair. So this is more electronegative atom. So it will have lesser tendency to give lone pair as compared to sp3 hybridized nitrogen. So highest basicity will be first, then second, then fourth, then third. So A will be your answer. Okay. So let's move to question number 21st. So this question is about sp mixing, and basically they have asked that which orbital will swap their energy due to sp mixing. So we all know that till N2 molecule. N2 molecules means 14 electrons. The molecular orbital diagram will be sigma 1s, sigma 1s star, sigma 2s, sigma 2s star, pi 2px, pi 2py, sigma 2pz, pi 2px star, pi 2py star, sigma 2pz star. So this will be the molecular orbital diagram for or till diatomic homonuclear diatomic molecules for till N2. Okay, but after N2, the molecular energy diagram will be sigma 1s, sigma 1s star, sigma 2s, sigma 2s star, sigma 2pz, pi 2px, pi 2py, pi 2px star, pi 2py star, sigma 2pz star. Okay, so the point is, if you can see the energy which has been swapped due to sp mixing, there is sp mixing till N2. After N2, there is no sp mixing. So after N2, you can say that the molecular orbital energy diagram should be or is like it should be. Like, so basically after N2, the molecular energy diagram, MOD, molecular orbital diagram, is like it should actually be. But before N2, because of sp mixing, this sigma pz, it just swaps the energy with pi. So this sigma pz goes after pi, like its energy increases as compared to pi 2px. Okay, so the orbitals which will swap their energies, that is what been written, molecular orbitals that swap their energies, right, are sigma 2p and pi 2p, sigma 2p and pi 2p, right? They have not given z or anything in any of the options, so we don't have to worry about that. But sigma and pi orbitals, sigma 2p and pi 2p orbitals will swap their energy due to sp mixing. So this is the case for sp mixing, right? So next question is related to again kinetics. So basically that is a potential energy diagram of the reaction, right? Reactant is given, product is given, so this is endothermic reaction, energy of product is more than reactant. The correct value of activation energy of backward reaction is, so obviously I told you that there is a forward reaction, then there is a backward reaction, just now we saw in catalyst question, right? So the activation energy for forward reaction will be the energy required by reactant to form the activated complex. So this will be activation energy of the forward reaction, EA forward, and the activation energy of backward reaction is the energy required by product to form the activated complex. So this will be activation energy of backward reaction. Now this activation energy of backward reaction is equivalent to Z, right? Activation energy of backward reaction is equivalent to Z, and this Z can also be written as Y minus X as per this graph. So whatever can be written in the options, you can see you have to check both. So in the options only Z is given, EB is equals to Z, not X plus Z. X plus Z will be this, okay? Z minus X will also not be the answer. X plus Z will not be the answer. X is the enthalpy of reaction, energy gap between product and reactant, right? So that is also not the answer. So EB is equals to Z is the answer. So next question. In this question, pre-exponential factor in the Arrhenius equation is given. We have already seen the Arrhenius equation, right? So Arrhenius equation is We saw earlier as well, right? I'll write it here again. Arrhenius equation is K is equals to A into e to the power minus EA by RT. Right, so this is your Arrhenius equation. So they have said they have given the value of pre-exponential factor. This is the pre-exponential factor A. Pre-exponential factor. Okay, the value of rate constant at extremely high temperature. So they have given the extremely high temperature value. So extremely high temperature means temperature will be tending to infinity. Whatever value, it is very high, so I can assume it to be infinity. What is infinity? Infinity is not something that you can't count. Infinity is something which is so high as per your standard conditions. When you compare with standard conditions, what is your standard temperature? What is your like normal room temperature, like 25 degrees Celsius, 30 degrees Celsius, 35. So for that, maybe 3000 degrees Celsius is infinite temperature. 30 and 3000, like 100 times temperature. So that is also infinite temperature, right? So that is what has been given. So temperature is tending to infinity here in this equation. So if temperature is tending to infinity, you can say that EA by R T is equals to EA by R into infinity, right? And anything divided by infinity is 0. So this will be 0. So this means that e to the power minus EA by RT will be equal to e to the power minus 0. Right, e to the power, anything which has negative power will go into the denominator. So e to the power minus 0 will be 1 by e to the power 0. Anything to the power of 0 is 1, right? So e to the power 0 is 1. So this will be 1 by 1, 1. Right? Right? So this whole term, e to the power minus EA by RT at very high temperature, infinite temperature is 1. So at T is equals to infinity, K is equals to A into 1. So K will be limiting at A, right? So value of K will be almost equivalent to your Arrhenius constant. So the value of rate constant at extremely high temperature will be closest to this only, 1.6 into 10 to the power 12 per second. There is one more concept that can be asked if they ask, okay, let it be. I'm not going to tell that because it might confuse you, but okay, you know how to put the limits. If they say that the value of rate constant at very low temperature, right? So at very low temperature, what will happen? So low temperature will be almost equivalent to 0. So temperature is tending to 0. So e to the power, or I would say EA by R0 will be infinity. Anything divided by 0 is infinity. So e to the power minus EA by RT is equals to 1 by e to the power EA by RT, and at temperature 0, this will be 1 by e to the power infinity. Anything raised to the power infinity is infinity. So 1 by e to the power infinity is equals to 1 by infinity. So that will be equivalent to 0, right? So at very low temperature, T is equals to 0 Kelvin. This whole thing, e to the power minus EA by RT will be 0. So K will be 0. So that is also a concept that can be asked. If a high temperature value can be asked, low temperature value can also be asked. So basically at this, K will be 0, tending to 0, right? So if something like that is asked, you know the answer, okay? So let's move to the next question. In this question, they are asking the number of optically active species. So obviously this is also a very important concept. Anything which is optically active compounds, you can see by two methods. First method is it should contain POS or COS. Anything, like you should check for POS or COS. You can check for POS, it's fine, it's better, right? It's easier. Second is that you should check for chiral center, chiral carbon. If chiral carbon is there, If chiral carbon is there, it is optically active. Third, you should check that it should not be meso. So any compound which is meso will not be optically active. So you should check for meso compound, it should not be meso, right? Secondly, you can check for POS. If there is a POS, then it will not be active, optically active. So it should not contain any POS or COS. And if it contains chiral carbon, it will be active, optically active. So you can see these compounds. So if you see the first and second compound, there will be a plane which will be passing through this compound like this plane. So it will just cut this compound. Even if you don't want to see plane, even if you don't want to see plane of symmetry or center of symmetry, you can see chiral carbon. So there is no chiral carbon here. Is there a chiral carbon? No, right? But the point is, it does not even contain, or it contains POS, plane of symmetry, right? So obviously, this will not be optically active. Similar to this, there will be a plane here, right? You can see a plane which is cutting the molecule right from the middle, right? Because the molecule is planar, right? So there is again a plane of symmetry, so this is also not optically active. If you see the third compound, see this carbon and this carbon. So in this carbon, one bond is hydrogen, one bond is this entire molecule, one bond is CH2, and another bond is this carbon, this group. So basically all four groups are different which are bonded to this carbon. So this is chiral center, right? Similarly, this carbon, one bond is this CH group, another bond is CH2 group, one bond will be hydrogen, one bond will be this CH3 group. So this will also be chiral center because there are four different bonds. So obviously there are two chiral centers, so this will be, and this is obviously not meso. So this will be optically active. Now, if you see this compound, fourth compound, you can see this center one, this one. So one bond is CH3, another bond is CH2, CH3, one bond will be H and one bond will be with this molecule, right? So basically four different bonds of this carbon. So this is also chiral center. So this is optically active. So only two compounds are optically active compounds here. Rest other compounds, both compounds contain POS, right? Okay. So in this compound we have to find the major product. So the first two reagents, O3Me2S, basically these reagents are for ozonolysis. So what does ozonolysis does? So ozonolysis will oxidize the alkene. Okay. So this alkene will break, one oxygen will be here, one oxygen will be added here. So that is what ozonolysis does. So after ozonolysis, after CH2O OH, so after O3 and Me2S, this bond will break, oxygen will be added, oxygen, OH and HH. So this will be the product. So after that you have to heat. So when you are heating it here, so this is beta keto acid. So this is alpha carbon, this is beta carbon. So this is acidic group, carboxylic acid. At beta there is a ketone. So beta keto acids, when they are heated, they undergo decarboxylation. Okay. So decarboxylation is a process of removal of this carboxyl group, COH group. Decarboxylation. So removal of carboxylic group. Okay. So what happens is, see. So this bond rotates. This bond rotates and OH comes here. So this will form intramolecular hydrogen bonding. So there will be a 6-membered intermediate that will be formed, kind of cyclic intermediate. So this will be the formation. So what will happen? This lone pair will then attack here, okay, and this bond will go here, and this will take hydrogen. Or I will. This bond will go here, not this pi bond, this bond. So when this oxygen lone pair will attack at this carbon, so this bond will break, this sigma bond, and this carbon will contain a negative charge, and so that will go and take this hydrogen. So what will happen? CO2 will be released, right? And hydrogen will be there, oxygen will be there. Okay, that will happen. So the final product will be your D product, if you can see. So you can see this D product, right? So this is your final product. So let's move to next question. So this question is about the colligative property. So basically non-volatile solute is dissolved in water. So colligative properties are properties which depend on the basically concentration, not the type of solute, but the concentration of solute, the amount of solute, right? So non-volatile solute is dissolved in water, causing boiling point of solution to increase. So boiling point of water is, first information is given, boiling point of water is 100 degrees Celsius, but the increased boiling point, TBF increased, is 100.25 degrees Celsius. So delta TB, increase in boiling point, will be TBF minus TBI. TBI is 100 degrees Celsius. So delta TB is 100.25 minus 100, so 0.25 degrees Celsius is the increase in boiling point. Now boiling point elevation constant Kb is given. What is the expected freezing point? So first use the formula for elevation of boiling point. So elevation in boiling point formula is delta TB is equals to I Kb M. M is molality, I is Van't Hoff factor. If Van't Hoff factor is not given, I will take Van't Hoff factor as 1. So Kb is given 0.512. This is 0.25, 0.512 degrees Celsius per molar and molality. From here, I will just calculate molality, 0.25, 0.512, right? So that will be your molality, right? So then what is the expected freezing point of the solution is if freezing point depression constant. Freezing point depression constant is given. So we need to find the expected freezing point of the solution. So use the freezing point depression formula, delta TF is equals to IKF M. M we have found from here 0.25 divided by 0.512. KF is given, I is 1. So KF will be 1.86 into 0.25, 0.512. So okay, I think that the options are not given completely. Let me check the options once. Okay, so option C here is minus 0.91, D here is minus 0.62. That is what the option is. 0.91, 0.62. Yeah, fine. So the point is this whole calculation will come out to be 0.91. So the formula of delta TF is freezing point of water, or the freezing point of initial like pure water, minus the freezing point of solution, because it is depression in freezing point. So freezing point of solution will be less. So you will subtract the less freezing point from higher freezing point. So higher freezing point is initial freezing point, which is your pure water. So freezing point I minus freezing point F final is equals to 0.91. So freezing point initial is 0 degrees Celsius. Water's freezing point is 0 degrees Celsius, right? Minus final is equals to 0.91. So final freezing point of solution will be 0 minus 0.91. So minus 0.91, right? So your answer will be C. Okay. So you need to find the freezing point of the solution, not the depression freezing point. You have to see what the question is asking. If they would have asked about the depression in freezing point, then it would have been plus 0.91, right? So let's move to question. Next question, which is magnetic moment 2.84 Bohr magneton is given by. So basically ions are given. So these are all 3D series ions, and you need to find the magnetic moment. See, if only magnetic moment is given, okay, so generally basically at your level they generally ask about spin only magnetic moment. So spin only magnetic moment formula will be mu s, spin only magnetic moment, root n plus 2, n is number of unpaired electron. So I will tell you a trick by which you can, if the value of spin only magnetic moment is given, you can approximate or you can predict the value of n. The point is whatever is the value of n, whatever, you just add 0.8 to 0.9 in that value. Add 0.7 to 0.9, okay, 0.7 to 0.9 to your n value to find mu s value. For example, your n 1, 2, 3, 4, 5. So add 0.7 to it, the value is almost close to 1.7 for mu s. Mu s, I am talking about mu s. Mu s, mu s, mu s, mu s. Spin only magnetic moment is close to 1.7 Bohr magneton. If the unpaired electron in your atom is 1, if it is 2, it is close to 2.8 or 2.9 Bohr magneton. I also don't remember the exact value, but it is close to 2.9, 2.8 Bohr magneton. Similarly, 3.8 Bohr magneton or 4.8. I am just writing the average value. I don't remember the exact values, 4.9 or whatever. I am just adding 0.8 in everything. Okay. Similarly, 5.8 Bohr magneton. Obviously, they also don't want you to remember the values. They want you to know the concept, right? So the point is 2.84 Bohr magneton value is given in the question. I don't know the exact, spin only magnetic moment values, but I know that if it is close to 2.8, I know that the number of unpaired electrons will be 2, right? So if you see nickel 2 plus here, so nickel 2 plus is D8 system, right? So this is not some crystal field given, or it is not a compound given, it is just the ion. So you just fill 8 electrons in d orbitals, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8. So basically you have n is equals to 2 unpaired electrons, right? So because of these 2 unpaired electrons, the spin only magnetic moment for nickel 2 plus will be close to 2.8. So your answer will be nickel 2 plus. You can check all other, you won't find the answer. In all other ions, the unpaired electrons will be less or more than 2, whatever, but not 2. Okay. So let's move to next question. In this question, we have to convert primary alcohol to nitrile, right? So OH is converted into CN, and 2 methods are given, and both of the methods are SN2 pathway. SN2 pathway means in this CN will attack from backside and OH will be released. So CN will substitute OH, right? In this, first OH will take H plus and convert into OH2 positive, right? So basically here the leaving group is OH, here the leaving group is H2O positive. So this is a better leaving group than OH. Obviously H2O is a better leaving group than OH. Right? So basically now CN will come and attack at backside, and H2O will leave. So obviously rate of SN2 reaction, any SN2, we saw the rate of SN1 reaction, so any SN2 reaction, you can see here, SN2 reaction. So if Rx is there, so there will be a nucleophile. So this nucleophile will attack from the backside and this leaving group will leave. So nucleophile R plus X minus. So this will be a concerted reaction. And the point is the rate of reaction depends on both Rx and nucleophile. That is why it is second order reaction. Those of you who know kinetics, K Rx 1 nucleophile 1, right? So this is a second order reaction. So obviously rate of reaction depends on Rx as well as nucleophile, and in Rx there is X, right? So the point is rate of reaction is directly proportional to leaving group tendency again. Like SN1, here also rate of reaction of SN2 is directly proportional to leaving group tendency. So higher is the tendency of this X to leave, more will be the chances of nucleophile to attack at the backside and substitute the X. So more will be the rate of reaction. So obviously K2 will be greater than K1 because in K2 the leaving group is much stronger, much better, right? So next question is basically we have to find the isomeric relationship between them. So this is again Fisher projection. So in Fisher projection, see, you can write these two rules. In Fisher projection, if there is a exchange of two groups, okay, first one is exchange of two groups. If that happens, it changes the absolute configuration. So R and S are changed. Okay, whatever is R will become S, whatever is S will become R. Second, exchange of three groups on a carbon atom. So on a single carbon atom, three groups are exchanged. So R will remain R in that case, S will remain S in that case. R will remain R, S will remain S, nothing will be changed. So if you see the first and second groups or first and second structures, in first carbon, in that carbon, this carbon, OH and CH3 are exchanged in this compound. So obviously whatever will be the configuration of this, let's suppose this is R, I am supposing this is R, this will be S. I don't know. I don't even have to find out. In the next carbon, second carbon, first CH3 and OH will be exchanged. So CH3 will come here, right? Then if OH is there, this OH and ET will be exchanged. So ET will come here and OH will come here. So there are like three exchanges, three groups are exchanged. So whatever will be the configuration of this, So whatever will be the configuration of this, it will stay same. So I am assuming this is R, I don't know if this is R or S. If this is R, this will remain R. So basically in both the compounds, two chiral centers are there, right? The configuration of one of the chiral center is same, but the other is different. So it will be diastereomer. Obviously, even if you want to find out, you can find out. So first, second, third. So 1, 2, 3 and fourth. So fourth configuration group is horizontal. So this is coming S, but this will be R. So my assumptions were right. This is actually R. So now this first, second, third. So again the configuration will be opposite. So it will be S. That's what I told you. Then this first, second, third. So fourth position is horizontal. So it will be opposite. So this will again be R. Wow. So my assuming powers are very strong, right? And then first, second, third. So this is S, this will again be R. So I told you. We didn't even have to find. We could just have gone by the rules and the answer will be same. Okay. So these are diastereomers. So then let's move to next question. Basically, this is a real van der Waals gas equation is given, P plus AN square by V square into V minus NB is equals to RT. We all know that this equation, right? So SI units of A and B. So the point is here we'll apply principle of homogeneity. Principle of homogeneity. This says that if two numbers are being subtracted or added, their dimensions or their units will be same. So A and B are subtracted or added, whatever. Let's say this is XY. X and Y are added or subtracted. Then dimensions of X and Y will be same. And obviously we can apply logic as well, no? The point is P plus AN square by V square. So P is pressure. So anything that will be added to pressure will be pressure, no? Anything that will be subtracted to pressure will be pressure. You can't add or subtract energy from pressure, or you can't add or subtract force from pressure or something like that. You can add pressure to pressure, no? For example, a particular pressure is being applied. You will add some more pressure to increase the pressure. It's not like you will add some more energy. Obviously you will apply more energy or something, but the point is what is added? Added is pressure, not energy. Are you able to understand me? So P plus AN square by V square. So AN square by V square should have the dimensions of pressure. So it should have the unit of ATM, obviously. So if the unit is ATM, so unit of N is mole square. Unit of V is liters square. So this entire unit is ATM, right? So unit of A will be ATM. Wait. Liter square by mole square. Similarly, V minus NB. So unit of NB should be that of volume. So it should be liters. So N is mole into B is equals to liter. So unit of B is liter per mole. So correct answer will be B liter per mole, A ATM liter square by mole square, right? So A is your correct answer, right? Okay, so let's move to the next question. Okay, so this is the answer. I have, rather than drawing, I have just prepared something so that we don't waste time on that. But the point is, which of the following sugars do not undergo muta rotation, right? So what is muta rotation? So I told you a concept here. In the first question itself, I told you a concept. Which concept? Where is the first question? Wait. This question, I told you that the open chain structure of glucose or any sugar will convert into closed chain structure, which is hemiacetal structure or something like that, right? So basically when open chain converts into closed chain, it converts into anomers, alpha anomer, beta anomer for glucose, right? Okay, so the point is when this glucose in solution converts from open chain to hemiacetal structure, like anomeric structure like alpha anomer and beta anomer. So these alpha anomers and beta anomers can interconvert into each other. How they can interconvert? So point it is this oxygen, when its lone pair attacks at carbon, right? So it forms hemiacetal group. Now what can happen? I am just explaining, okay? What can happen? This lone pair of oxygen can again attack at this carbon. Which carbon? Carbon it is attached to this one. It can attack, and then this bond of oxygen will break, and this oxygen will take this OH, right? And it will again convert into open chain, then it will again convert into closed chain, and this time it will form beta anomer. This can happen, and it is evident, it happens, okay? So the point is that closed chain structure, hemiacetal structure or anomeric structure of glucose or various other various other sugar molecules or carbohydrate molecules. Basically, these hemiacetal structures, they interconvert between different anomeric forms. And the point is, if you see, these anomeric forms will have different optical rotations. Okay, so alpha form will have different optical rotation, beta form will have different optical rotation, and because of their distribution in the solution will have some optical rotation, right? Because let's say alpha has x optical rotation and beta has y optical rotation, and in the solution, because there is rapid or continuous interconversion going on between alpha and beta, let's suppose in the solution the ratio between alpha and beta is 1:3, whatever, I don't know. So if that ratio is 1:3, then one part of the solution will have x optical rotation, and three parts of the solution will have y optical rotation. So the overall optical rotation will be 3y minus x, so whatever it is, right? Whatever will be the value. So that is how the optical rotation of the solution is decided. But the point is, because of this rapid and continuous interconversion between these two forms, this ratio between alpha and beta form will change. Okay, it will not be constant, and because of this changing of the ratio or composition of the solution, the optical rotation also changes. That is known as muta rotation. Okay, mutation of rotation. It means changing of rotation. Rotation means rotation of plane polarized light, which means changing of optical activity of the solution. So muta rotation is a phenomenon in which optical activity of solution changes. Change of optical activity, change of optical rotation due to interconversion between anomers, or you can say hemiacetal forms of sugar molecules. Okay, now the point is, which sugar or which carbohydrate molecule cannot undergo muta rotation? Obviously, whose oxygen I told you, na? Like I told you this. So if this oxygen is not free, its lone pair is not free, right? It is not free. So it won't be able to attack at this carbon, and this won't be able to convert into open chain structure and won't go into this beta form. Again, simple, it's very logical. So the point is, if you see sucrose, here, so it is formed from glucose plus fructose. So alpha enomer of glucose and your fructose, like hemiacetal form of fructose only. So this OH and this OH, they will go condensation reaction, H2O will leave, and this oxygen will be bonded to both glucose and fructose molecules. Okay, are you able to see? Right? So this oxygen is not free like in this glucose molecule. This oxygen is free, it has hydrogen bonded to it, right? So basically it can attack, right? Obviously this oxygen can take its hydrogen, right? But here no hydrogen is present. Even if it attacks, what will this oxygen take? Nothing. So obviously this hemiacetal form can convert into open chain structure, but this form of sucrose, where two hemiacetal rings are joined of glucose and fructose, this oxygen can't now go back to the hemiacetal form of glucose or fructose or whatever. So the point is, sucrose can't undergo to open chain structure again. You will have to do hydrolysis, specifically a different chemical reaction. It won't undergo into open chain structure like automatically. So obviously if it can't undergo into open chain structure, so it won't undergo Mutarotation, so no mutarotation. Simple. All other forms are just monosaccharides, glucose, maltose, lactose, whatever. But sucrose is a disaccharide in which oxygen can't attack again and can't be converted into hemiacetal form again. So all other molecules are fine, but sucrose won't undergo mutarotation. Its optical activity won't change. Whatever is the optical activity of its solution, it will be like that only. Okay. So let's go on to the next question, right? The next question is from structure of atoms, right? So in this question, wave function versus distance curve is given, okay? And we have to find the number of angular nodes. So this question I also put this question in the IIT Mega Mock of your crash course, if you remember. So I believe that this question is important, okay? Because maybe not this question, but the concept is important. So if it won't ask the number of angular nodes, it will ask the number of radial nodes. And generally in these kinds of questions, it asks, or the examiner asks, the number of radial nodes only. So if you know, the examiner tries to modify the question and instead of number of radial nodes, it gives angular nodes, then how to solve this question, right? So if the examiner would have asked about the radial nodes, right? So radial nodes is simply those who know that radial nodes is the number of times the curve touches the x-axis of this curve. Okay, right? So this is the wave function versus your radius curve, right? Radius means distance from the nucleus, right? That's what we are talking about. So the number of times this curve that touches the x-axis is the radial nodes. For this graph, radial nodes will be 1, right? But the point is, in the question, the examiner is not asking about the radial nodes. He is asking about the angular nodes, right? So to find the angular nodes, you have to find the orbital first. So if you know this thing, how to find the orbital, then. So the point that I want to tell is that for s orbital, only for s orbital, for any other orbital it is not valid, but for s orbital at nucleus means when r is 0. So when r is 0 at nucleus, the wave function is non-zero. Okay. For s orbital at r is equals to 0, wave function is not 0. Okay, and if wave function is not 0, which means it will not start from the 0. So basically, if you see this is 0, let me rub this. This is your 0, this is your origin, which means r is 0 here, which means this is nucleus. So at nucleus, the wave function is not starting from 0, if you see. Starting from 0 means it would have started from here, or it would have started from here, something like that, right? But the point is, it is not starting from 0, it has a non-zero value, right? So obviously, this is s orbital we are talking about. Okay. Now we don't know about the principal quantum number. We don't know about the n, but we know about the L, right? L is 0. So if L is 0, number of angular nodes is equals to L value. So angular nodes is equals to L value. So angular nodes here, you can say, will be 0. So radial nodes is 1 for such graph, but angular node is 0. Why? Because this is s orbital. Okay. So such quotient can be modified like that. Okay. And if it is not modified, you should know how to find radial nodes using this curve. Okay. So let's move on to the next question. So again, this is a question which contains the topics of equilibrium as well as electrochemistry. So this kind of question is kind of important. I think that it can be asked. If not this question, but the concept can be asked, like E naught values and equilibrium values and all that stuff. So in this question, we have to find the equilibrium constant. We have been given electrochemical equation. So this is the electrochemical reaction in which indium 2 plus is being oxidized to indium 3 plus and copper 2 plus is being reduced to copper plus. Okay, so we know the oxidizing and reducing species. Now at 300 Kelvin, we have to find the equilibrium constant from the given values of standard electrode potential. So standard electrode potential values are given, right? So we have to find that. So from standard electrode potentials, we can find the standard cell potential, right? So standard cell potential will be E naught cell is equals to E naught cathode minus E naught anode, right? So indium 2 plus to 3 plus. So cathode is copper 2 plus to copper plus. E naught copper 2 plus to copper plus, right? Minus anode is indium 2 plus to 3 plus. So anode is oxidation, but we have to find the reduction potential, because in general, like for convention, we use reduction potential, right? So we want to find E naught indium 3 plus to indium 2 plus, right? So E naught copper 2 plus to copper plus is given, E naught indium 3 plus to plus is given, indium 2 plus to indium plus is given, but indium 3 plus to 2 plus is not given. So here we will find the indium 3 plus to 2 plus value using Latimer diagram. So Latimer diagram, I might be writing the wrong spelling, so forgive me, but the concept will be fine, right? So in Latimer diagram, you can do anything. Either you write the most oxidized form on the left, or you write the most reduced form on the left. And if you are writing the most oxidized form on the left, you will write the most reduced form in the right. Okay, so most oxidized form of indium in this question is indium 3 plus. Then most reduced form is indium plus. So middle form is indium 2 plus, right? So okay, so basically there are three situations. First, from where we are going from indium 3 plus to indium 2 plus, we are reducing from indium 3 plus to 2 plus. So indium 3 plus to 2 plus we have to find, right? Then indium 2 plus to indium plus reduction is given, indium 2 plus to indium plus. So E naught value is minus 0.50 volt. .50 volt. Wait. Right? And how many electrons are gained? 1 electron. So N value is 1. Right? Similarly, from indium 3 plus to indium plus, value is given minus 0.56 volt. And N value is 2, because 2 electrons are gained from going from indium 3 plus to indium plus. Now we have to find this E naught value, which is X. Let's suppose this E naught value is X. I am assuming this is X. Okay. And indium 3 plus to 2 plus, N value will be 1, because only 1 electron is gained. So we can write from Latimer diagram from here, this whole value 2 into minus 0.56 volt is equals to this value plus this value. So is equals to 1 into X plus 1 into minus 0.50 volt. Okay, so we can write 2 6 12 minus 1.12 volt is equals to X minus 0.50 volt. So this will be plus, so this will be 1.12 0.50, right? Wait, 6, yeah, so 0.62 minus 0.62 volt will be X. So 0.62 volt will be X. So this is the reduction potential from indium 3 plus to 2 plus, this one. Okay, so from here we will find the E naught value, E naught cell. It will be E naught copper 2 plus to copper plus 0.25 volt minus of this value 0.62 volt. So this will be plus. So this will be 7, 8, right? 0.87 volt is the standard cell potential E naught value. Now from that we need to find what? We need to find equilibrium constant value. So we can use the Nernst equation. Nernst equation E cell is equals to E naught cell minus 2.303 RT by NF log K equilibrium. Right? So E naught cell value we have calculated 0.87. E cell value is 0 at equilibrium. At equilibrium, this value is 0 obviously, and this is E naught cell is equals to 2.303 RT by NF log K equilibrium, right? So point is, when temperature is 298 Kelvin, this whole value 2.303 RT by F becomes 0.059. Here in the question temperature is 300 Kelvin. So value will be close to 0.059. So we can assume it to be 0.059. So this E naught cell value will be 0.059 divided by N log K equilibrium, and N value is the number of electrons involved in the balanced electrochemical equation. So balanced electrochemical equation is this: number of electrons involved will be 1 by, because indium 2 plus is losing 1 electron to form indium 3 plus, so copper 2 plus is gaining 1 electron to form copper plus. So N is 1. So basically E naught cell, which is your 0.87 volt, will be 0.059 log K equilibrium. So from here you can find the K equilibrium. Log K equilibrium will be 0.87 divided by 0.059. Then K equilibrium will be 10 to the power whatever is the answer. So the point I want to say is, concept is this: calculations can be wrong. This calculation might be wrong, but this is Latimer diagram. This is how you find the reduction or redox potential or oxidation potential, whatever reduction potential or oxidation potential of the redox couple that is missing, right? So that is how you find that, and then from that you find E naught cell, and from that you find K equilibrium, and calculations you can manage whatever. The answer will be 10 to the power 15. Okay, the concept is this. The purpose of solving this question is because such type of questions contain two or more topics together in one question. Like equilibrium is asked in this, electrochemistry is asked in this, Latimer diagram is asked in this. So this is a very good question. So you need to know all these concepts. Okay, so let's move further. So statements which are incorrect as per VBT. So VBT is the valence bond theory obviously of the chemical bonding. So it is a good question again. So we have to find the incorrect statement. The first statement is VBT does not support excitation of 2s electron to 2p in the formation of trivalent nitrogenous compound. Basically what is happening here, 2s electron to 2p electron nitrogenous compound. Okay, so in nitrogenous compounds, for example, whatever compound you want to take, let's take NH3. Okay, so if you see nitrogen, okay, so its valence electronic configuration is 2s2 2p3. Okay, so it is saying that this s electron need not to be excited to p electron for bond formation, and that is fine, because excitation only happens when we need unpaired orbitals, right? And excitation only happens when there is a vacant orbital, ahead. So here there is no 2d orbital, right? If there would have been a 2d orbital, then excitation would have happened, maybe. But point is, we don't have to think about it because there is no 2d orbital. And in NH3, in compounds like NH3, NF3, whatever, so 3 sigma bonds are needed to be formed, and 3 sigma bonds will be formed using these unpaired orbitals. Okay, so there is no need of excitation. So first point is right, it is not incorrect. So this is right. Second one is valence bond theory focuses only on central atom as far as its bonding mechanism is concerned. Obviously, in valence bond theory, we see the central atom. Like in NH3 as well, we are not seeing hydrogen. We are only seeing the central atom. We find the hybridization of the central atom. Hybridization is a concept for central atom. It says that the orbitals of central atom, they mix together to give rise to hybridized orbitals, okay, of the same energy, right? But it is only for central atom. So we find the steric number for central atom and all that stuff. We don't see the side atom, whatever it is, hydrogen, fluorine, chlorine, whatever. So this is again a good or not good but correct statement. Statement C, without the presence of hybridization, 3 CH bonds out of 4 in methane must be orthogonal to each other. That is also right. If you see carbon, if you see CH4 and you see carbon, 2s2, 2p2, right? Then one electron excites, so it becomes 2s1, 2p3, right? Now the point is, they are saying if these orbitals would not have hybridized to form 4 equally energized hybridized orbitals like sp3 orbitals, then this would be s orbital and this would be p orbital, and these p orbitals are at 90 degree to each other. So whatever bonds these 3 p orbitals will make, like in CH4, so 3 hydrogen will form bonds with these 3 p orbitals. So these 3 bonds will be 90 degree to each other because 3 p orbitals are 90 degree to each other. So they are orthogonal. 90 degree is orthogonal, okay? Okay. So that is what has been said. So this is also right. So only option incorrect is D. So that is what the limitation of VBT was, that it said that O2 is paramagnetic. Why it said O2 is paramagnetic? Because in O2 it didn't consider molecular orbital theory or something like that. It just said that in O2, in oxygen, the valence electronic configuration is 2s2 2p4 2 3 4. So only these 2 orbitals are unpaired orbitals. So of the second oxygen atom as well, in O2 there are 2 oxygen atoms. So for the second oxygen atom as well, 2 unpaired orbitals will be there, 1 2. So these two unpaired orbitals and these 2 unpaired orbitals will just bond together. So these electrons will pair up. That's what VBT said. So it considered O2 as diamagnetic. Okay, it didn't consider anything about MOT. And we know from MOT that O2 is paramagnetic, right? Its HOMO is pi star. Pi star or pi? I think pi star. Whatever it is, we can form the MOD, but whatever it is. But the point is O2 is paramagnetic, but incorrect statement as per VBT. So VBT considered it as diamagnetic. So as per VBT, O2 is not paramagnetic. So that is the incorrect statement. So let's move to next question. In this question, basically we have to find the number of quaternary carbons. Okay. So there are 3 types of carbons or 4 types of carbons. So any sp3 hybridized carbon, see, sp3 hybridized carbon atom. So basically in any sp3 hybridized carbon, the carbon attached to one carbon is primary, carbon attached to 2 other carbons is secondary, carbon attached to 3 other carbons is tertiary, and carbon attached to 4 other carbons is quaternary. So carbon attached to only one carbon is primary, carbon attached to 2 carbons is secondary, carbon attached to 3 carbons is tertiary, carbon attached to 4 carbons is quaternary. Now what will other bonds be? You must be thinking that if this carbon is attached to one carbon, what will other bonds be? It can be anything except carbon. Okay. So in this molecule you can see any sp3 hybridized carbon which has a quaternary last, right? So any sp3 hybridized carbon which has 4 carbons attached to it. So I can see this one. So 1, 2, 3, 4. 4 carbons are attached to it. Similarly this carbon, 1, 2, 3, 4. Similarly this carbon, 1, 2, 3, 4. So these carbons are sp2, these one, okay, and this carbon is also sp2, this carbon is also sp2, this carbon is also sp2. So we won't see these carbon 1, 2, 3, 4, 5. These 5 carbons you won't see. Among these carbons 1, 2 and 3 is quaternary. This is not, this is not, this is not okay, this is not okay, this one okay. So only 3 carbons. Which carbons? This one, and this one. They are quaternary carbons. Okay. So let's move to next question. So this is a good question. Basically, there will be a lot of concepts in this one question of organic chemistry. So basically, we have to find the Q, and after Q, we have to find the total chiral centers in the product Q. Okay. So first reaction that you can see here is your PDBSO4 and H2, and there is acyl chloride, right? So acyl chloride's reaction with PDBSO4 and H2. This is Rosenmund reaction, so it will be converted into aldehyde. So after PDBSO4, H2, after first, the product will be aldehyde, right? Then NaBH4 dry ether. So NaBH4 will convert this aldehyde into, primary alcohol. NaBH4 dry ether. So this hydride will attack here and O minus will open up. Then after that H3O plus is also given. So H3O plus will do the acidic workup. So the final result after both these steps I am writing is your primary alcohol, right? After that KOH and HCN is given. So KOH, so OH minus is provided by KOH and HCN. So this OH minus will take this H plus and Cn minus will be left out. So this Cn minus will do SN2 reaction here and substitute OH, alcohol group, right? So cyanide will be formed, right? So this cyanide, obviously H3O plus is also added for basically after this formation of cyanide we need to do acidic hydrolysis. H plus H2O, H3O plus means H plus H2O. So acidic hydrolysis of this cyanide group, right? So we know that it forms your acid. So first C double bond O NH2 will be formed, then H2O will again attack on it, so it will become COOH. So you need to revise again these questions will tell you which mechanisms you need to revise again, right? So basically I am not here to do the complete mechanisms. So I am here to tell the questions, which questions can come. You need to revise the mechanisms like hydrolysis of cyanide and all that stuff, okay? So after that ETMGBr, dry ether. This is Grignard reagent, Grignard dry ether. So this ET will attack here, this will open up, then it will come back and OH will be removed, and basically again, okay, so this will be ET, okay. Now the point is H3O plus is given. Are you able to understand me? So this H3O plus means we have to do acidic workup. So this product we don't need to do acidic workup. So obviously there must be another ETMGBr who will attack here. How? See. Again, if ETMGBr will be attacking, so it will again attack here. So this will open up. Then this will become O minus. So now O minus needs acidic workup. So this last step, H3O plus, is a hint. Basically, ETMGBr is not written in excess here, but the last step H3O plus is a hint. We can't do just acidic workup like that. We need some negative charge, something to neutralize. So basically, this O minus will open up. After this opening up of O minus, the last step H3O plus will neutralize this O minus, and this will become your OH. Okay. Now the point is 2 ET are added, 1 ET and 1 ET. So 1, 2, 1, 2. Okay. So we need to find the total number of chiral centers. Okay. So if you see this one, so let's see any carbon. Let's see this carbon. Maybe this carbon is chiral, but OH and 2 ET are added, right? So if 2 ET are added, two same groups are added, it won't be chiral. Now let's see this carbon, this one. So basically one group is this group, another group is this CH2, then one is hydrogen and one group is this. So this carbon is your optically active. Okay, so this your chiral center. And is there any other carbon? If you see this one, so one group is CH3, okay, then another group is CH2, then another group is this CH, and then one is hydrogen. So this will also be chiral center. So, and I don't see any other group which is chiral. So basically 2 chiral centers will be there in product Q. Is this fine? Okay, so let's move on to next question. So basically we need to find the product P and Q in this one. So this is again, first one is your Cannizzaro reaction, because it is concentrated at NaOH and then there is no enolizable proton here. So basically this concentrated NaOH, I am not going to tell the mechanism here, will attack here or here because both are symmetric. It can attack anywhere. So one will be formed as your carboxylic acid or the salt of carboxylic acid, and another will be alcohol, but then again there is H3O plus. So one will be carboxylic acid. Let's suppose this is carboxylic acid, this P is, let's suppose this P is, this is just general Cannizzaro reaction. So this one will be carboxylic acid and the upper one will be alcohol. I'm just assuming whatever it can be. So this is your P product. After that we have to attack with OH minus. So I'm not again explaining the mechanism of Cannizzaro. It is a very common reaction. If you guys don't know, just revise that. Okay. So OH minus, I will write the reaction here, Cannizzaro. Forgive me for the spelling if it is wrong, but whatever it is. So if now I am adding NaOH, so what will happen? This is NaOH and aqueous, right? So basically this is your basic medium, OH minus along with water, right? So basic medium along with water, alcohol and acid is present. So what will happen? Esterification. Esterification can happen both in basic as well as in acidic medium. Generally it happens in acidic medium, but it can happen in basic medium as well. So OH minus will take this also, will take this also, both, right? It's not like it will just take acidic proton, it will take the alcohol's proton as well, it is also acidic, right? So this alcohol will attack on this, and I will explain the mechanism there. Wait, maybe. What will happen? OH minus. So this will take its hydrogen, this will attack on oxygen, this will go up, this will come back, and OH will be left there, and this OH will take this hydrogen. Okay, so ester will be formed. Okay, this kind of ester is formed. No, there is not. There is one less carbon than, right? So this should be the final answer, final ester. Now the point is, you guys must be thinking that why is this H still on, because I told that this OH minus will take the acidic hydrogen, but there is H2O as well, right? There is H2O as well. So it will take this H plus, this will be O minus, but to leave this has to be a good leaving group. So then while leaving, it will take the H2O H positive, right? So don't worry about that. So this will happen, esterification will happen. So your answer will be something like this. Okay, so you can see I just did the reverse. So they in the answer they have said that this will form the alcohol and this will be acid. So if this will form the alcohol, so ester will be upwards, not downwards, and the product will be same. So your answer will be D. Okay, so let's move on to next question. In this question we have to find the or identify the given reaction. So this is a kind of a good question. IIT might ask this kind of questions or this kind of concepts. Your concepts should be clear. So this is your Grignard reagent, right? This is isopropyl MgVr. So this isopropyl will then attack on your ketone. This will open up, and after that acidic hydrolysis is there. So this will become OH and isopropyl group is added. So the point is this isopropyl is a nucleophile, and we all know carbonyl group is electrophile. So this carbonyl group is electrophile. This isopropyl is nucleophile. So this nucleophile attacks on this and nucleophile is added on this. If there would have been a leaving group, this nucleophile would have added and that leaving group would have left. That would be a substitution reaction. But here nothing is leaving. This nucleophile is just being added. So this is nucleophilic addition reaction. Okay. So nucleophilic addition, not nucleophilic substitution. Okay. So nucleophile is being added to the substrate. If electrophile would have been added to the substrate, it would have been electrophilic addition. Okay, so whatever is being added to the substrate, we will see that. Okay, or whatever is being attacking on the substrate. The reagent is attacking on the substrate, so the reagent is nucleophile, so it will be nucleophilic reaction, substitution or addition, whatever it is, but it will be nucleophilic. That should be constant. So reagent is nucleophile. I am just writing here so that you remember that. Therefore, the reaction will be nucleophilic. Okay, that is the convention that we follow. Okay, so let's move on to next question. Okay, so this is a good question. So in the given graph, which of the following graph represents the correct variation of bond order with total number of electrons for homodiatomic molecules? This is not homidiatomic, this is homodiatomic. It is spelling mistake. It's okay. Consider no sp mixing. So we don't have to consider any sp mixing. See, we don't have to consider sp mixing. So if you would have considered sp mixing, then till 14 electrons, like up until N2 molecule, homonuclear diatomic molecule. I told you in this previous question as well, one of the previous questions as well, like before N2 or till N2, there is sp mixing. So then pi and sigma pz orbitals, swap their energies, 2pz orbitals and 2px and 2py orbitals, they swap their energies, pi, right? So the point is here, no sp mixing is considered, so there will be no swapping of energies. So the configuration will be just like O2. O2 means after N2. So the configuration will be no sp mixing. So this will be sigma 1s, sigma 1s star, sigma 2s, sigma 2s star, sigma 2pz, pi 2px, pi 2py, pi star, 2px, pi star, 2py, sigma star, 2pz. Okay, so this is the electronic configuration. Then starting from 8 electrons, number of electrons are 8. So if we are going to fill 8 electrons, 2, 4, 6, 8. So basically, number of electrons in bonding molecular orbitals is equals to number of electrons in anti-bonding molecular orbitals. So bond order will be 0. So in 8, I am writing bond order and number of electrons. 8, 9, 10, 11, 12, 13, 14. So in 8, bond order is 0. So as 1 electron more will be added, so it will be in bonding molecular orbital, sigma 2pz. So bond order will be 0.5. Bond order will increase. Then 2 electrons will be added to sigma 2pz. So bond order will increase by 0.5 as well. So bond order is increasing per electron, 0.5 bond order is increasing if the electron is going into bonding molecular orbital. If the electron will be going into anti-bonding molecular orbital, so per electron 0.5 bond order will be reduced. So this will be 1 bond order. Then 11 electrons again in the bonding molecular orbital, so 1.5, 12, 2.0, 13, 2.5, 14, 3. So till 14, from 8 to 14, it will be bond order will increase from 0 to 3. Then 15, 16, 17. Okay, 15, 16, 17, 18, 19, 20. So 15, from 15 till 14, pi 2px and pi 2py are completely filled. From 15, first electron will go into pi star, anti-bonding molecular orbital. So bond order will start reducing from 3, 0.5 and 0.5. So it will be 2.5. So now the order will be reverse. 16, 2.0, 17, 1.5, 18, 1.0, 19, 0.5, 20, 0. So if you see from 0 to 3, then 3 to 0. So the curve is something like this. Are you able to see? From 8 up till this point, 14. It is starting from 0 and going up till 3, maximum bond order. And then from 14, it is just reducing to 20 by 0. So from 3 to 0, right? So that is how this question will be analyzed, right? So this is a good question. Okay. So let's move to next question. So in this question is regarding osmosis and reaction mechanism. So again, kind of two topics are asked in one single question. So this is a good question. So it might be asked, it might not be asked, but the point is osmosis and some questions which require common sense can be asked by IIT. So FeCl3 reacts with K4 FeCN6 in aqueous solution to give blue color. So they are saying that FeCl3 plus K4 FeCN6, it reacts and give blue color. Whatever product it is giving, I don't know, but it is giving blue color solution. Blue color, right? So the point is, if these two are separated by semi-permeable membrane as shown in the figure, then due to osmosis. Now what is osmosis? So osmosis is movement of solvent molecules from low concentration region to high concentration region, right? To balance the concentrations. Okay, so concentration will be decreased as solvent will move from low concentration to high concentration region. So in high concentration region where solute particles are more, concentration will decrease because solvent is going, right? So the point is osmosis is movement of solvent molecules via or through semi-permeable membrane. SPM, I'm writing semi-permeable membrane, whatever it is. So the information to note here is that only solvent molecules will be moving. So solvent molecule here is water, I'm assuming. Okay, so aqueous solution is given, right? So solvent molecule is water. So only water will be moving from here or here, I don't know. So only water is moving. So if water is moving, how will the reaction be happening? Reaction will be happening when FeCl3 will be moving from here to here, or K4 FeCN6 is moving from here to here. That's the only situation where they both will react and the solution will become blue. But the point is they are not moving, they are just separated. Only solvent is moving. So if solvent is moving, FeCl3 and K4 FeCN6 won't even react. Right? If they won't even react, no blue color is formed, no blue color will be seen. So this question, there might be less tendency of this question to come, but the point is the motive to keep this question was, this question if you see, it was just a common sense question. You only needed to know what is osmosis, that's it. That's it. So this was not very advanced question, but by seeing this might seem a very advanced question. So sometimes IIT or NIST or these kinds of exam, they give these questions to trap the students. But the point is, in reality, those questions are very easy questions. If only you apply your mind and if you apply your common sense. Okay, so be ready for such kind of questions as well. Okay, so let's move to second question. Yeah, so basically in this question, so this question might trick you a bit. Okay, this question might trick you a bit. So in this question, MS values are 0 plus 1 minus plus half minus half the number of elements in 9th period we have to find. Okay, so first of all, let me rub all of this. Okay, so these are the things that I do in my adult time. So don't be shocked about this. Okay, don't worry. So see, if MS is magnetic spin quantum number, right? So not magnetic quantum number but spin quantum number. Okay, MS. So the point is, when ms values are 2 plus half and minus half, so that means that in one orbital 2 electrons are present, both with opposite spins. One will have ms value plus half, another will have ms value minus half. But in this question it has said that ms values are possible 3. Now along with plus half and minus half, one value that is 0 is also possible. So that means if 3 ms values are possible, one orbital will now contain 3 electrons. That can happen, and that will happen. That is the motive of giving 3 values of ms, right? So the point is, number of elements in any period is equal to number of electrons that can be filled in that period, if you analyze that properly, right? So number of elements in any period is equals to number of electrons in that period. And how can we find the number of electrons in any period? We find the number of orbitals in any period, we multiply it by 2. But the point is, in this system, 3 electrons can be filled in one orbital. So we'll see number of orbitals in any period into, we'll just multiply by 3. Okay. So we have to find the number of orbitals first in the ninth period. So I will give you a trick. And I will give you some other thing. Because you won't be able to know how many orbitals are there or how many subshells are there in ninth period. But the point is, in exams they won't go up to ninth period. If such question comes, they will go up to the period, like the periods which are available in periodic table, like up to 7th period, so that you will know how many orbitals are there. But if they give you ninth orbital or ninth period, whatever, so this is the orbital filling diagram. If you can see, this is in NCERT, you can see from there as well. Why am I giving this to you? To make you understand something. So if you continue this 1s, 2s, 3s, 4s, 5s, 6s, then 8s, then 9s, then 10s, then here if you continue 5g, because in 4 G subshell is not available. Why? Because G subshell L value of G subshell is 4. So in any shell, in any nth shell, maximum L value can be n minus 1. So in 4th shell, maximum L value can be 3. So maximum orbital available for not orbital, subshell available for 4th shell is 4f, not 4g, right? So 5g can be possible from for 5th shell, then 6f, 6g, 7d, 7f, 7g, 8p, 8d, 8f, 8g, 9p, 9d, 9f. So one thing you have to realize, that any shell, any basically period, not shell, any period opens or starts from S subshell and ends at P subshell in periodic table. If you can see, okay, this is periodic table, right? In this periodic table, this is S subshell, S block, this is P subshell, P block. So any period, first, second, third, fourth, fifth, will start from S and end at P. You have to keep that in mind. Okay. Anyways, yeah. So we need to find what? Your ninth shell. So 8th shell will start from 8s here. So it will go like this. And 9th shell will start from 9s here. So it will start from 9s. Then 6g, 7f, 8d, 8p, and 10th shell will start from 10s. So in ninth shell, or ninth period, sorry, not shell, in ninth period of your periodic table, whatever subshells will be there, 9s, it will start from S obviously, then 6G as per energy values, then 7F, okay, then 8D, then at the end 9P. So that is how you can, calculate the subshells that are possible in ninth period. But obviously, this far won't be asked. Maximum to maximum first period, second period, third period, fourth period, fifth, sixth period will be asked. Not ninth, but still. So 9S, 6G. So I will write 9S, 6G, 7F, 8D, 9P. 7F, 8D, 9P. So we need to find the number of orbitals. So number of orbitals in 9s is 1 orbitals. In 6G, so G is L value 4. So orbitals are 12 plus 1. So 9 orbitals. F 7 orbitals. D 5 orbitals. P 3 orbitals. So 1 plus 3, 4, 4 plus 5, 9, 9 plus 7, 16, 16 plus 9, 25. So electrons, 25 into 3, 3 5s are 5, 175. So number of electrons is equals to number of elements in that period. So the answer will be 75. Okay, is that fine? So let's move to next question. Basically in this question we have to find the correct structure of PF3Cl2. So in PF3Cl2, obviously if they would not have shown the structure, we would have to find the hybridization, steric number, and then geometry, and then all of that stuff. But in this question they have already given the geometry, right? If they would not have given the geometry, you would have to find the geometry that it is TBP, trigonal bipyramidal. Steric number will be 5, so you would have needed to calculate the steric number. But here you don't need to do that. Here you know that the geometry is TBP, trigonal bipyramidal, and in TBP you know that at axial positions more electronegative atom comes, and axial position more electronegative atom, and electronegativity of fluorine is more than chlorine, we all know that. And at equatorial position more bulky atom comes, more bulky atom or groups. So bulkiness is more for chlorine as compared to fluorine. Chlorine is more bulky as compared, it is bigger than fluorine, right? So basically at axial positions 2F will be there from 3F. So if you can see 2F are there on axial position, and 2Cl of the Cl2 are at equatorial position. In all other structures you can see that is not the case. So basically only one is your correct option. This will be the most stable form. Okay. So right. So let's move on to next question. In this question basically we have to give the total number of stereoisomers, right, for the given compound. So the formula for total number of stereoisomers is total stereoisomers is 2 to the power n, where n is number of achiral centers or number of optical centers. Number of achiral or optically active centers. Okay, so number of optically active centers. In optically active centers you will see two things. The first one is achiral carbon, the carbon with 4 different bonds. We have discussed in this in this video what is a chiral carbon center. So carbon center with 4 different bonds. So chiral carbon center is your optically active center. Second, any pi center, basically any pi bond, any carbon center which contains a pi bond, single pi bond between two carbons. So single two carbons sharing a pi bond. And then there are other things as well, like chirality, access and all that stuff, but that is not in your syllabus, so that might not be asked by IIT. So these two things can be asked by IIT. So if you see two carbon centers sharing a pi bond, or if you see a carbon center with 4 different bonds, so basically these are your optically active centers and this will be value of n. So in this question, one is this, second is this, like 2 carbons sharing a pi bond, right? Third is this, and 2 carbons sharing a pi bond, but the point is they should have geometrical isomerism. Here the condition is geometrical isomerism is possible. So you need to what? Revise geometrical isomerism as well as optical isomerism after this session. Okay. So geometrical isomerism is possible. So for geometrical isomerism, the two groups on both the ends of carbon sharing a double bond should be different. Like basically cis and trans can be done, or basically E and Z can be identified there. If all the groups connected to C double bond C are same, like C double bond C, H, H, basically 4H are connected to it, so it won't be optically active, it won't show geometrical isomerism. So basically here, like 4 groups on C double bond C are different, right? Here H and H, basically this is trans, then obviously there will be EZ configuration here, again here there will be EZ configuration, again here there will be EZ configuration. So these are optically active centers. Okay, and if you see any other thing, any other carbon is not present which is a chiral carbon center in this. You can see any carbon which there will be no carbon which will have 4 different bonds. Okay, so n value is 4. So 2 to the power 4 will be 32. So total number of stereoisomers is 32. Okay, for this compound. Okay, so let's move to next question. So this is your next PYQ. It might come, it might not come, but the concept can come. Okay, so basically following molecular orbitals are formed by sidewise overlapping of p atomic orbitals, 2p atomic orbitals. So we have to arrange them in correct energies of molecular orbitals. So the point is, if let's suppose you see first, so these are all p orbitals. This is a p orbital, right? And this plus and minus is just the electronic wave phase. That's it, right? So plus minus means we all know that if the electronic wave is in one particular phase in the above orbital, above lobe of the orbital, in the below lobe, it will be in the opposite phase altogether. Okay, so the point is, when the orbitals, the lobes of the orbitals with the same phases are parallel to each other, so there will be constructive interference. So these all orbitals will constructively interfere. Okay, there will be constructive interference, and the electron density is shared by all 4 of the orbitals, like between all 4 of the orbitals. So it will be the case of this. See, this is pi bond, this is pi bond. Okay, pp. So basically this electron density is basically delocalized. Basically these 4 electrons, these 4 pi electrons are delocalized between these 4 p orbitals without any node. There is no node. Okay, so this is the case for first. So this pi electron density will be more stable in first. Now if you see second, there will be a node. When two lobes of opposite phases come together parallel to each other, they destructively interfere and there will be a node. A node is a position where electron density is 0. So if there is a 0 electron density, so this situation is like this. So this is p, this is p, p, p. So these 2 pi electrons are here, these 2 pi electrons are here, but between them there is no delocalization because there is a node here. So electron can't go from here to here. Are you able to understand me? So there is less here there is a pi bond because two same phase orbitals are adjacent to each other, but here and here there is a node. So this is a situation like this. I would say like this. Okay, so this will go here, resonance will be done. So this might be positive, this might be negative. So here and here there will be a node. This electron density is here. Okay, so this might be a situation of this molecule. So obviously this molecule is less stable than other two molecules, right? And if you see the third molecule, so here everywhere there is a node, if you can see. So this situation is like this. So basically there is no pi bond here. So basically plus minus and then plus minus. The situation is just like that. So electron density is just there. There is no bond because there is all destructive interference. So if there is a destructive interference, so bond is not formed between these two orbitals or these two orbitals or these two orbitals, whatever. So this is anti-bonding molecular orbital, if you see. Okay, so this is complete anti-bonding, right? So this will be least stable. So third is least stable. So energy will be most for third. So stability inversely proportional to energy. So energy will be most for third. So these two options can be correct. These are not correct. After that fourth. So fourth, then second, then first. So basically most stable is first, so its energy will be lowest. Least stable is third, its energy will be highest. So C is your answer. Okay. Okay. So let's move to next question. In this question we have to find the major product P and Q. So basically this is your, so PHCHO is non-ionizable carbonyl group, basically non-ionizable carbonyl compound, right? So only carbonyl compound which can be ionized here is CH3COH. So this will be ionized. So this will become CH2 minus when OH minus will take that hydrogen and it will attack on this carbonyl. So this will be H OH PH. Okay, so after first PHCHO is added, the product will be like this. Then there are two more hydrogen atoms. So again OH minus will take this hydrogen atom. Again it will attack at PHCHO. So just like that, it will attack two times from this hydrogen as well. So basically two more these substituents will be added. So the final product after all of this will be when these ionizable hydrogens will be exhausted, the final product will be OH, PH, PH, OH, PH, OH. Okay, this is the final product. Then after that 3 PHCHO molecules are consumed. 1 PHCHO molecule will still be left. So plus PHCHO and OH minus will be there. So then OH minus will either attack at this carbonyl or will attack at this carbonyl. So this carbonyl is more electrophilic. Why this is more electrophilic? Because this does not have any pH. So here pH is providing some plus R effect first of all. So it does not have a direct connection with any pH. Then there are these OH groups. Which will apply minus I effect. So this will be more electrophilic carbon. Okay. So this OH minus will attack here. So this is a Cannizzaro reaction. First one was like a aldol reaction, not aldol. Aldol, cross aldol you can say. But this is a Cannizzaro type of reaction. So basically, what will happen? This will be O minus, then this will be O minus. I am not drawing the substituent. This is R, whatever it is, right? And this is H. So this O minus will come back. So this H will then attack at carbonyl carbon. So this is the mechanism of Cannizzaro, obviously. So this will become your alcohol. PHCHO will become your alcohol, and this will become your carboxylic acid. So basically in the options there is no carboxylate ion, so obviously I am assuming that there is a hydrolysis there. So basically the final product will be OH, then OH, pH, OH, pH, OH, pH, and then pH, H will be there, so CH2OH. So this will be PHCH2OH, right? So your product will be, I think this, if you see A, so A has pH COOH, so this is wrong. This is also wrong. This and this can be right. In this, your 3 PHOH groups are there, 4 PHOH groups are there. So this is also wrong. So only option is this. So okay, here they are giving your K, carboxylate ion they are giving. Okay, this is fine. So basically 3 PHOH groups and one is COOK and one is PHOH, PHCH2OH, right? So basically this was a good question, but the point is this question might not come or might come, but you have to understand the aldol and Cannizzaro and all that stuff, right? Cross aldol and all that stuff, right? So now let's move on to next question. So okay, basically in this following process we have to find the correct statement. Okay, so obviously we know that when we react phenol with zinc dust and heat it, it will become benzene, right? We all know that. So this is phenol. Phenol is also known as carbolic acid. Carbolic acid or phenol. So we are reacting it with zinc dust and heating it, so it will become benzene. Okay, so this is P. So P is going back to phenol by X as per the question. Okay, so correct statement is P is not toluene, so this is incorrect statement. P is not carbolic acid. Carbolic acid is your this phenol. P is not carbolic acid. P is benzene. So carbolic acid can be obtained from P via. So basically they have given the mechanism of X. So let's see what X is. So carbolic acid can be obtained from P via nitration. Okay. So if you are doing nitration of benzene, okay, so obviously they want to make phenol. So I would just assume that this is mononitration, not trinitration or something. This is controlled nitration. So if you are controlling the nitration in not very extreme conditions like using dilute HNO3 and all that stuff, so what will happen? Only one NO2 will be added. So this is nitration. Then Stephen's reduction. Stephen's reduction is SnCl2 and HCl. So this will convert NO2 into NH2. Right? After that, diazotization is there. NaNO2 and HCl. NaNO2 HCl. So this NH2 will convert into N2 plus and Cl minus, obviously. Right? After that, we have to heat it in ethanol. So when you are heating it to ethanol, it will convert into benzene again. You are just heating it in ethanol. Nothing else will happen. This diazotization N2 plus Cl minus will remove. So if you wanted to make it phenol, you should have added H3O plus instead of heating it in ethanol. Ethanol won't do anything. It will just remove the N2 plus and Cl minus. So this will just give you benzene back. So this is the wrong statement, then obviously not this one, then obviously the right statement is D1. So without even checking, we can write D is correct. Array. But the point is we still have to see. So basically, series of reagents in X is your isopropyl chloride in anhydrous AlCl3. So this is Friedel-Crafts alkylation, right? So benzene reacted with isopropyl chloride in AlCl3. So this will be Friedel-Crafts alkylation in benzene. So this isopropyl will be added to any carbon, whatever. So this is benzene, isopropyl benzene, whatever it is. So cumene you can write, right? So after that they are giving oxidation in air, so obviously O2 will be added. So the point is there is a hydrogen here. So this oxygen, 2 atoms will be added between these hydrogen and carbon. Are you able to understand? So this will become OOH. So this is cumene hydroperoxide. Okay, so this cumene hydroperoxide, when you do acidic hydrolysis, H3O plus, so this whole thing will be removed. Okay, so ketone will be removed and your phenol will be formed. Okay, so you can form phenol back from this method. This is Hawk's process or Hawk method. Okay, so your correct statement is D, obviously, right? So this again is a good question, can be asked, might not be asked, but concept can be repeated, so that is the thing. So in this question we have to find the increasing order of reactivity towards LDA at minus 78 degrees Celsius for all these protons HA, HB and HC. So LDA is lithium diisobutyl amide. Okay, so LDA, we all know that it is a bulky and strong base, very strong base and very bulky. So if there is a acidic proton in a particular molecule, so tendency of that proton to leave depends on its acidity and also depends on the bulkiness of the base. What I am saying, tendency of H plus to leave depends on first what? Its acidity, or by acidity I mean to say like how convenient or how much is the tendency for that H plus to leave, and greater the stability of conjugate base after leaving of that H plus, more will be its tendency to leave. So I will say stability of conjugate base, second bulkiness of base. Maybe a particular H plus or particular hydrogen has very high tendency to leave, because after its leaving conjugate base will be very stable, but the base is very bulky and it is just in very crowded environment. Hydrogen is in very crowded environment, so base won't be able to reach that hydrogen, so it won't be able to take that hydrogen. So LDA, as I said, it is a bulky base. So what will it do? It will take, or the tendency of LDA to take a hydrogen will be at less hindered side. So will prefer less hindered hydrogen. So if you see hindrance, as per the steric hindrance, HC is least hindered. So least hindered right, and most hindered is HA. Sorry, see there are two CH3 groups here, and one carbonyl group here. So it will hinder LDA from attacking at HA. So most hindered HA, and HB is in the middle of something between HA and HC. HB is there. So the point is, the highest tendency of LDA is to take HC. Okay, so increasing order of reactivity, so HC is most reactive for LDA. It doesn't matter, maybe HB is the most acidic proton, because after HB is leaving, this minus charge will be stabilized by 2 minus M effect, right? So this is active methylene group. So maybe this is most stable, this is most acidic proton, but this is hindered as compared to HC. So when HC will be going, this minus charge will be stabilized by only 1 minus M effect. So this is stable, this is acidic proton, but not as acidic as this B. Okay, but the point is, LDA is a very bulky base, so it will prefer this HC proton. So the tendency of reacting with LDA will be more for HC and least for HA, least reactive. And obviously in the middle will be somewhere in the middle of both of them will be HB. So HC, HB, HA. This is the reactivity order. Okay, if instead of LDA there would have been H minus, KH is the base. KH is the base. So KH is not a bulky base. It is a small base, very small compared to LDA. So it will just see the most acidic proton. So it would have taken this first. So reactivity will be most for HB in that case. Okay, so these are the concepts of general organic chemistry. So again, this is a sign to revise all the acidity, basicity and reactivity orders, right? So then let's move to this question. This question is basically based on specific optical activity, right? So this question is not asked in IIT till now, but the point is optical activity can be asked, right? If not in IIT, maybe in NEST. So this is 50 most important questions for IIT. So maybe there is a chance. Okay, so the point is butane 2-ol has two forms. RNS, optical activity is given of 0.1 gram per ml. RNS butane 2-ol filled in a 0.1 decimeter cuvette is 0.34. Specific optical activity of R enantiomer is asked if its enantiomeric excess is given. So the point is, first we need to find the specific optical activity of the solution. So optical activity of the solution is equals to specific O naught, this theta naught is specific optical activity of the solution into C into L, right? So C is concentration, L is the length of the cuvette, okay, in which the solution is whatever stored or kept. So this optical activity, specific optical activity will be optical activity of the solution divided by C into L. So this optical activity of the solution is given 0.34 plus 0.34 degree. Concentration is taken in this formula. Concentration is taken in gram per ml and length is taken as decimeter. So you don't have to convert into any other unit. If this would have been given in some other unit, you would have to convert into gram per ml and 0.1 and decimeter basically. So basically concentration is given in 0.1 gram per ml and then length is 0.1 decimeter, right? So you need to do this. Let's suppose this is your x, the value of your theta naught, specific optical rotation is x, okay, of the solution. So if specific optical rotation of the solution is x, how to find enantiomeric excess? So your enantiomeric excess will be what? EE I am writing, percentage EE. So percentage enantiomeric excess is your specific optical rotation of the solution divided by specific optical rotation of enantiomer which is in excess. Okay, in 200. So specific optical rotation of solution is x. For enantiomer it is given, we have to find for enantiomer, right? When it's enantiomer, and enantiomeric excess is given 41%. So 41% is your enantiomeric excess. We have to find the specific optical rotation for enantiomer. So you just need to first calculate x, then you need to calculate this enantiomer optical rotation, specific optical rotation of enantiomer will be x by 41 into 100. If you will calculate this, this will come out to be 34. Okay, so your enantiomeric excess, you can do the calculation. So your optical rotation, specific optical rotation will be 82.92 plus 82.92 for plus r. The answer might be different, I don't know, I don't remember the calculations and all. You can do the calculation, but the hint for you here is to revise this concept. So because each and every year something new is asked, obviously they won't repeat each and every concept from the previous years, something new is asked. So basically maybe this concept is asked, maybe, because optical activity and optically active compounds, basically stereochemistry, these are very important topics. So this topic is not yet asked and this is in your syllabus, so maybe it is asked this year. So do this, okay. So let's move to the next question. So basically again, IUPAC nomenclature is not yet asked in IIT, but NEST is asking, slowly and steadily NEST is asking IUPAC nomenclature in its exams, right? You can see the PYQs as well. So the point is, you know, maybe IIT also decides this year that, okay, we will also ask something from IUPAC. So, and even if they are going to ask, they might not ask the simple IUPAC, they will maybe mix some concepts. So this question is just like that. So I also put this concept in your IIT Mega Mock, right, if you remember. So in this question, basically we have to find the IUPAC nomenclature along with the configuration of the chiral centers. So again, stereochemistry is there and IUPAC nomenclature is there. So again, this is a hint, this is a call for you to go and revise IUPAC nomenclature and stereochemistry. Okay, so first we need to find the configurations. Okay, so let's find the configurations. So if we find these two are the chiral centers, right? So if we find the configuration of this 1, 2, 3, so this is your R configuration, but the point is H, fourth configuration, fourth priority group is at horizontal position in your Fisher configuration, so your absolute configuration will be reversed. So this will be S. Similarly, 1, 2, 3. This is R, but again, fourth priority group is horizontal configuration, horizontal position, so basically configuration will be reversed. So this will also be S. So this is S, this is S. Now the point is, chlorine and hydroxy groups, they are not functional groups as per IUPAC. As per IUPAC, they are substituents. So, and substituents have equal priority, right? So if they have equal priority, which substituent should get the lowest number? So we will decide that according to lowest locant rule, but the point is OH and Cl are substituents, not functional groups. And as per IUPAC, I am not saying it is not functional group, it is as per IUPAC, for IUPAC nomenclature, it is not, they are not considered functional groups, okay. But in reality, they are, okay. So they are substituents, not functional groups. Then we'll find the lowest locant rule. So as per the lowest locant rule, we'll do the numbering from both sides of the chain. So this is the chain, 5-membered chain. So let's do the numbering. 1, 2, 3, 4, and 5 is also here. And if we do from here, 1, 2, 3, 4. 1, 2 will be here. This will be 3, this will be 4, this will be 5. So as per the lowest locant rule, if we go from down to up, the first substituent will come at 3. But if we go from up to down, the first substituent will come at 2. So the lowest locant rule says that we'll do the numbering from that side, from where the first substituent will get the lowest number. Okay, so as per lowest Locant rule, the name will be, so 2 chloro, 1, 2, 3, 4, 5. So 2 chloro, 3 hydroxy, okay, then pentane, right? So 2s, 3s, right? So basically this will be 2s, 3s, 2 chloro, and we will write chloro first. Why? Because chloro is starting from C and hydroxy is starting from H. So chloro is dominant alphabetically as well. So 2 chloro, 3 hydroxy pentane, 5-membered ring. Not ring, sorry, chain. So A is your answer. Okay. So revised nomenclature. If not asked in IIT, it might be asked in NEST. Okay. So revise it. Okay. And obviously there might be other exams also that you must have filled. So in other exams this question might be asked. Not this question, but IUPAC is very important. So basically revise IUPAC. Okay. Don't leave it. So then this is the last question, I think, right? Or whatever. So basically in this question we have to again find the major product S. So this is a very good question. I put this question in the IIT Mega Mock as well. So basically as per this question we need to find the role of PCC. So PCC is pyridinium chlorochromate. So it is a mild oxidizing agent, if you know. Mild oxidizing agent. So it oxidizes 2 degree alcohol into ketone and 1 degree alcohol into aldehyde. So P will be, this P will be ketone, aldehyde. Okay. After that, they have given the protecting group. Okay. So CH2, CH2, OH, OH, right? So we have to protect this OH, OH. So this is P. Now the point is this is nucleophilic group and it will attack on the most electrophilic group, and most among aldehyde and ketone. This is very common. Most electrophilic group is aldehyde. So it will attack on aldehyde. So they both will attack on aldehyde and they will just form the acetyl group. So it is protected. Now this is wait aldehyde, no? H. Okay. So now this is Q. After that they have added Grignard reagent MEMGBr, and then they have done the acidic hydrolysis MEMGBr, second is H plus. So this Me will now attack at the ketone and O minus will take this H plus. The O minus will open up, it will take the H plus. So the product will be OH, and obviously there is H3O plus, not just acid but acidic hydrolysis. So this acidic hydrolysis will deprotect this as well. So this will convert into again aldehyde, right? So this is your R, and then after that NaBH4 and ETOH is there. So NaBH4 will again reduce the aldehyde into 2 degree alcohol, 1 degree alcohol, sorry. NaBH4, ETOH. So this will be OH, OH. So your S is your final product is your S. So what will this be? OH, OH. So this is your B, if you see. Okay. Okay. So again, so basically we have already done this question in IIT Mega Mock as well. So this is again some of question of organic in which language is given, and you have to identify the product or the reactant or whatever, some species using the language. So such type of questions are very favorite for JEE level exams as well, and IIT is somewhere close to JEE mains. Okay, so it might ask the language questions this time. Nest asks it. Nest generally asks that question or these kinds of questions, but IIT never asks these kinds of questions. Maybe once or twice it has asked, but it might ask this time. So maybe we can do that. So this is just one question. So again, it is a hint to go and check these kinds of questions. You must have your question practice for these kinds of questions as well. So an organic liquid is there, P, which is containing CHNO with the boiling point 78 degrees Celsius. So it possesses a pleasant odor. Heating with concentrated H2SO4 gives a gaseous product Q with empirical formula CH2. So this CH2Q, it decolorizes bromine water, which means it contains a pi bond. So obviously decolorizing a bromine water test is the test for unsaturation. So this is an unsaturated compound first of all. So first information is CH2 is unsaturated, right? The second information is it takes up 1 mole of H2. So 1 mole of Q will take up 1 mole of H2. So obviously when one pi bond is broken, we saw this in previous question as well, like hydrogenation of pi bond. So obviously pi bond is broken and 2 new hydrogen bonds are formed. So not hydrogen bonds, 2 new sigma bonds with hydrogen are formed. So this one bond will be broken and 1 mole of hydrogen will be attached like this. So obviously this molecule contains only 1 pi bond. If 2 pi bonds would have been there, so 2 moles of H2 would have been required, right? So that is the information. Second information, CH2 only contains 1 pi bond, and these two informations are enough to find the P and Q. So P is your molecule with 78 degrees Celsius boiling point, and we know one such species with 78 degrees Celsius, 78 to 80 degrees Celsius boiling point, that is ethanol, right? So if you, I don't know if it is ethanol or not, but if I am assuming it to be ethanol, so let's take it as CH3 CH2OH. So 78 degrees Celsius boiling point. From this information I am assuming that, completely from this information. Then on heating with concentrated H2SO4, this is dehydration reaction, it will give you Q. So just dehydrated H2SO4 heat. Dehydration means minus H2O. Water is lost from there. So if H2O is being lost from there, this OH will be lost and this hydrogen, one of the hydrogens will be lost. So this will become CH2 double bond CH2. So its molecular formula is C2H4. So if its molecular formula is C2H4, its empirical formula will be CH2. So this is Q. This is your P. So this Q is unsaturated. It contains 1 pi bond. So basically all the things are matching here. So if you see the option, C2H5 is P, C2H5OH is P, and C2H4 is Q. If you match any other option, C2H5OH on dehydration won't give C2H2. It won't give ethine. It will give ethene. Only one H2O molecule will be left, will be released. Then CH3OH. This is not methanol. Methanol does not have 78 degrees Celsius boiling point. And again, C2H5 is what is C2H5, right? So again, this can't be the answer. Then CH32CHOH and C3H6, like, it's making no sense. C3H6 does not contain any pi bond. This is alkane. This is your propane, not propane. Sorry, this is propene, C3H6, right? But then again, there are 3 carbons in that, and maybe there is a pi bond, okay, but CH3 to CHOH. Okay, so this is this molecule, CH3 OH, this molecule. So obviously this molecule will again not have 78 degrees Celsius boiling point. So yeah, so basically in such type of questions, all the informations are necessary. So you need to read the question properly, each and every question. Okay. So basically this was your 50 most important. So let's just quickly analyze all the questions. So this was your language based organic question. I'm quickly analyzing, I'm quickly revising, so that you need to know what to revise, not just these questions but the concepts. So language based organic questions you need to revise. Again, organic reaction mechanism you have to revise. IUPAC, please do that, please. IUPAC and stereochemistry, don't leave that. And this optical activity, enantiometric excess and all that stuff, make a note of that and revise that. And then again, a GOC, LDA and all that stuff, you need to revise these things. Again, reaction mechanism, organic, Hawkes process, and then this is aldol and name reactions you have to do. Okay, name reactions you have to do. Chemical bonding, molecular orbital theory is very important. Please revise that for chemistry. And then again, total stereoisomer, stereochemistry, geometrical isomerism, you have to do that. Then your chemical bonding, hybridization and all that stuff. This question was a bit out of the blue, so it might not come, but the concept can come, not from ninth shell but from any other shell. So yeah. So then again, osmosis, this type of question I told you that common sense questions can sometimes be asked. And again, chemical bonding, MOT, very important, very important. Okay, so again, so you need to know what type of reaction is there, nucleophilic addition, substitution. So make sure that your reaction mechanism concepts are fine. Then again, your Cannizzaro reaction, named reactions, right? So named reactions you have to do. Then again, Rosenmund reaction and all that. Rosenmund reaction I've written. So this is Rosenmund reaction. Again, named reaction. And then again, there are different reactions, different types of reactions in one question only. So certain type of questions can come. So you need to know each and every reaction. Okay. So then again, quaternary carbon and again GOC stuff. Okay. Then VBT, MOT, chemical bonding. I'm again telling MOT is very important. And then electrochemistry is important, Nernst equation and equilibrium. The questions in which two or more concepts are mixed together. Very good questions, they can come. So Nernst equation, make sure of that. Make sure that you revise that. And again, in structure of atom, you need to revise all these graph-based questions like radial nodes, angular nodes, and all that stuff. And then again, biomolecules, one or two questions are asked. Okay, so basically, generally most of the questions are from either carbohydrates or proteins, amino acids or carbohydrates. Like carbohydrates are like sucrose and glucose, mutarotation and nomers and all that stuff, and from proteins as well and amino acids. So make sure that you need to revise that as well. Then obviously these are physical chemistry. So physical chemistry you need to know, and stereochemistry relationships, and again SN1 SN2 reactions, very important, right? And similarly, magnetic movement, very important concept. Magnetic movement can be asked from coordination compounds, from your chemical bonding as well. Again, colligative property is also very important. Colligative property, make a note of that. You need to revise that. And again, see your ozonolysis, again a name reaction. So do that. Okay, don't miss these things. Again, how to find optically active compounds, POS, COS, chiral center, very important thing. And then pre-exponential vector, Arrhenius equation, one of the very important concepts of your chemical kinetics. Similarly, again, chemical kinetics, activation energy, Arrhenius equation, very important. Okay. Similarly, MOT, again MOT is very important here. Okay. So again, GOC, basicity, acidity, make sure to revise these things. Hydrogenation, enthalpy of hydrogenation, thermodynamics, right? So make sure of that. Aromaticity is a very important concept. Make sure to revise that as well. And then basically again, catalyst, activation energy, backward, forward reaction, equilibrium. So these things are important. Again, see this curve, this reaction coordinate curve, very important, potential energy curve. Okay, so make sure to revise that as well. And obviously, okay, this is something new. Okay, so graphs can be asked for colligative properties, cannot be asked, but make sure to revise colligative properties. If not graphs, revise them. Okay, colligative properties at least. Okay, then again, organic, that electrophilic substitution reactions, again reaction mechanism, don't leave that. Okay, similar to that, alkene, stability of alkene, one of the very important topics for your GOC. So you need to understand the Brett's rule, make sure that bridgehead carbon and all that stuff. Okay, so hyperconjugation effect, so make sure to revise that. And then coordination chemistry, synergistic bonding, important concept, can be asked. If not this, then these things, homo, lumo, bond order, anything from these can be asked. So coordination is also very important. Then again, your radical mechanism is important. Whenever there is UV, radical mechanism is there, so radical reactions can be there, so don't miss them. Okay, and your okay, so this is again GOC. Very sometimes simple questions can also be asked, like sp3 carbons and quaternary carbons. So don't make a mistake in these freebies. These are freebies. Okay, and then again coordination and DNF block, basically your atomic radii trend in DNF block, in D block, in F block. So this is important. Okay, so don't, and in coordination, lambda max is a very important concept. So make a note of that as well. And your again activated complex, activation energy, chemical kinetics, then electrochemistry, galvanic cell redox reaction, electrochemistry, spontaneous electron flow, anode cathode. Make sure to revise these things as well. So basically, and then your again SN1, SN2, you have to see the rate of reaction. So again, reaction mechanism, right? And then obviously Haworth projection and your Fisher projection, biomolecules, right? So basically you need to know that, right? I told you biomolecules, either carbohydrates or proteins, right? So at least revise these two things in biomolecules, carbohydrates and proteins, right? So this was your 50 most important IAT questions. So these questions, again, I'm saying it is not that I'm predicting the paper. It's not like these questions will be asked, but the concepts which is stored in all of these 50 questions, like 50 concepts, even if they repeat 7 to 8 concepts from this slide, from this video, it's just that you will be able to do 7 to 8 correct questions. Okay, so it might be helpful, right? So basically revise these concepts. These questions might not be asked, but concepts might be asked. But anyways, just revise everything at this last time. Be very prepared. Don't be nervous. You have done very good throughout the year, so don't be afraid. Just be happy and study more and more. Question practice is necessary. Do more and more question practice, and don't be afraid. Okay, it will be good, but don't be nervous. Okay, it will be good. So best of luck to you, and just see you in your dream institute. Okay, bye bye.